Good morning or good afternoon to everyone, depending on where you are. Welcome to another session of the advanced course in biomedical imaging. This course, as you know, is organized by the Faculty of Medicine of the University of Coimbra in collaboration with the UT Austin Portugal Program. Today's session will be completely in English. My name is Mara, and together with my colleague Adriana, we'll be representing the UT Austin program and giving technical support throughout the session. In the name of the program, I would like to thank all of you for your interest in the course and for participating in today's session. I also take the opportunity to thank our speaker for today, Professor Osama Mawlawi. Thank you for your availability to give today's lecture. I will now give the floor to today's moderators, Professor Salomé Pires and Margarida Branch, and wish you all a great session. Thank you.
Thank you, Mara. Welcome, everyone. Today's session, which is about PET, we have with us Professor Osama Mawlawi, and the three sessions will be performed by him. Professor Mawlawi is a tenured professor of imaging physics and the section chief of nuclear medicine physics at the University of Texas MD Anderson Cancer Center. His ongoing research is aimed at developing novel techniques for PET-CT image acquisition, correction, and reformation, as well as modeling the distribution of novel radiotracers. Dr. Mawlawi has extensive expertise in PET imaging of biomarkers, in preclinical applications, and in phase 1 to 3 clinical trials. He has authored over 100 peer-reviewed articles and book chapters, and is the recipient of several grants from industry and professional societies. The first session will be about the fundamentals of PET. Professor Mawlawi, the floor is yours.
Well, thank you very much. I truly appreciate the invite. This is the second year that I give these talks, and obviously I am very fond of that, and I am very happy to participate. Truly appreciate the invite again, and thank you for the presentation. So the first talk today is about the fundamental principles of PET imaging. PET stands for Positron Emission Tomography. I have nothing to disclose at this time. The learning objective of this presentation is to understand the basic physics of a PET scanner, what is construction, what are the various components, what are the principles of its operation, the corrections that we apply, and then talk briefly about PET-CT imaging. The field of PET imaging has evolved from dedicated PET scanners to being hybrid systems such as PET-CT. There are no more manufacturers that develop PET-only scanners. They all develop hybrid scanners, PET-CT type systems. So one of the first important concepts that we need to understand is that PET imaging is a functional imaging modality rather than a structural or anatomical imaging modality. What do you mean by function? By function, we mean that you can see images whereby you can see blood flow or glucose metabolism or receptor binding. So you can see that the images are not characterized by showing anatomy, but rather showing an underlying biochemical or a physiological type process. The principle works in a very similar manner to a regular gamma camera. You inject a radioactive tracer to image a chemical or a biological process. This radio tracer decays by positron emission. That's where the name PET comes from, because the decay schema of the radionuclide is by positron emission. And then when the tracer is introduced into the body, its site-specific uptake can then be traced by means of that radioactive or labeled type atom. So we start by administering the radioactivity into the patient. It distributes inside the patient. The nucleus decays by emitting a positron. It interacts with an electron, and the positron and the electron, because they are two antiparticles with respect to each other, they transform their mass into energy by producing then two photons. We call that a annihilation photon. And these two come out as two annihilation photons that are about 180 degrees apart from each other. And these photons are then detected by detectors that surround the patient. So these yellow dotted lines here represents the scanner, and the detectors that are in the scanners then detect these annihilation photons. This happens constantly inside the scanner because you are injecting the radiopharmaceutical into the patient, and this radiopharmaceutical is decaying constantly inside the body. So there will be annihilation photons that are generated constantly inside the body, and the detectors around the patient will be detecting these annihilation photons regularly throughout the imaging session. These annihilation photons then are reconstructed. There are different reconstruction techniques. We will not talk so much about image reconstruction here. This is an old slide showing image reconstruction using filter back projection type technique. But then the idea is to generate an image that looks like what you are seeing here on the right side, that depicts the distribution of the radiopharmaceutical that was administered into the patient in different areas of the body, with the understanding that areas that have high uptake or areas where the radiotracer is accumulating more implies that these are areas that have high affinity for the drug that you have administered. PET images are acquired in the axial direction. Then you put all of these slices together, and then you can slice them in different direction, either coronal or sagittal direction. And then you can display the images in a maximum intensity type projection images. Let's go through this process a little bit in much more detail so that we understand really how this principle really works. So when we talked about the annihilation photon happening, the mass of a positron and the mass of the electron is then transformed into energy using Einstein's famous equation, E = mc squared. If you replace m here by the mass of the positron and the mass of the electron and multiply it by the square of the speed of light here, the total energy that will be generated will be equal to 1.02 MeV. 1.02 MeV, mega electron volt, is the total energy. But this energy appears, as we said, as two annihilation photons, this one here and this one here. And because the energy is divided equally between these two annihilation photons, then each one of them would be equal to 511 keV. So it's very then important to note that in PET imaging, whatever you administer to the patient, whether it's a radiopharmaceutical that is labeled with fluorine 18, carbon 11, nitrogen 13, oxygen 15, copper 64, gallium 68, all of these will decay by positron emission. And then the energy that will be generated will always be equal to 511 keV. So it's independent of the radioactive atom that we are administering into the patient. This is very, very different than in gamma camera, regular gamma camera, whereby the radionuclide has a specific energy, and it is that particular energy that we are ending up imaging. Like for technetium, you look at 140 keV, your thallium or indium or iodine, and so on and so forth. Very different energies that we're going to be looking at compared to PET imaging that we're always tuning at 511 keV. So that's a fundamental difference between PET and gamma camera type imaging or SPECT type imaging. The other thing that is very fundamentally different is that I had mentioned that the annihilation photons, whenever they occur, there are going to be two of them that gets to be generated at the same time. That implies that there is a line along which these two annihilation photons gets to be generated. This line is known as the line of response. It's very important that in a PET scanner, we get two annihilation photons, and their path represents the line of response through which the annihilation photons are traveling. So then the balance of PET imaging is to try to identify these lines of response as they occur in the PET scan during the imaging session itself. So then we need to talk about how do we identify these lines of response. We call that line of response determination, we need to identify if each annihilation event get to be detected by the detector, check its energy to see if it's equal to 511 keV. We call that photon or singles detection and processing. We need to also identify whether if an event occurred on this detector, there is also another event that occurred on another detector to create that line of response. And these should happen at exactly the same time. Like I had mentioned previously, both of these events, this one here and this one there, occur at the same time. So that means that this detector that detects this event and this detector that detects that event should be detecting these two events relatively at the same time. That is known as coincidence imaging. That's why in PET imaging, we need to assess coincidences, whether these two events occurred at the same time or not. So other than detecting the events, we need to check to see if they occurred at the same time or not by coincidence events. And then we need to store the data and queue it for image reconstruction. So these are the three different steps that we need to look at whenever we are trying to determine this line of response. So let's first go back to figuring out how do we detect the single photon for every annihilation event that happens. That actually also is multiple steps. So we first need to detect the event itself and transform the annihilation photon into an electronic pulse. We need to check its energy to make sure it's equal to 511 keV. We need to identify its location, determine its location. And then we need to identify the time at which it arrived so that we can compare to see if another one that is relatively diametrically opposite to it occurred also at the same time or not. So several events needs to happen here in order to say, yes, we have a single photon event, annihilation photon, that we should keep track of or not. And we will go through these events one after the other. So let's talk about the event detection. We say whenever an annihilation photon occurs, it needs to be detected by the detectors. The detectors that are used in a PET scanner needs to be relatively dense because the energy of this incident photon is relatively large, 511 keV. So you need to have a detector that's relatively dense so it can stop the incident energy onto that detector. The type of detectors that are currently used in PET scanners are either lutetium oxyorthosilicate or bismuth germanate oxide. So these are relatively dense type detectors, and they are known as scintillators. The idea of a scintillator is very similar to a gamma camera, whereby if an energy is deposited into a scintillator, that energy is transformed into light, and that light is then transitioned into the detector and then detected by another electronic device known as a photomultiplier tube. The light falls onto the photomultiplier tube. The light then falls on what we call the photocathode in here. The light then transforms into electrons. These electrons are then multiplied through the various diodes that are in the photomultiplier tube. They are multiplied, so the signal is actually increased in order for us to be able to measure it using electronic type circuits. So there are multiple stages in the photomultiplier tube, and you can see these stages cause the signal to increase. And this increase is proportional, actually. So we will get to have a signal intensity at the output here that is equivalent to the amount of light that is falling onto the detector. And the amount of light is proportional to the amount of energy that is in the incident photon. So this whole process is relatively a linear process, and the signal intensity that you see at the output here should be proportional to the incident energy that is falling onto the detector itself. So that is the purpose of this detector, to transform energy into an electrical signal. And it is done into two stages, first by transforming energy into light, and then light into electrons, and then the signal gets to be multiplied into a proportional manner. Like I said, we use different type of scintillators in a PET scanner. The reason is that the density, as you can see here, the density, which is how hard is that particular detector element so that it can stop the 511 keV photons, it's relatively much higher than it is for a gamma camera. As you know, in a gamma camera, the detectors are more made from sodium iodide, and you can see here the density is much, much, much lower. Also, the atomic number is much higher than it is in sodium iodide. That means that the stopping power of these detectors are much higher than the stopping power of sodium iodide. The reason why we look at different type detectors is because they have different performance characteristics other than them being relatively very dense and can stop the incident photons relatively efficiently. The difference between them is the speed by which they generate this light. You can see here that BGO and GSO are relatively, they generate relatively little light compared to LSO. However, they are also relatively slow in the way that they can respond to an incident type photon compared to LSO. Most of scanners right now that are available commercially have detectors that are made out of LSO or LYSO. It's relatively the same type detector. But General Electric has just recently started to introduce again BGO type scanners into the market. BGO is much, much cheaper than LSO in order to make scanners because it is much easier to actually construct and to build type such type detectors. This is a relatively old slide showing how do we arrange these detectors. So this is here a block of BGO detectors or LSO detectors that is attached to a bunch of photomultiplier tubes. So you can see here a block of detectors attached to multiple photomultiplier tubes here, and then they are packaged here into a module whereby these are the detector blocks, these are the photomultiplier tubes, and so on and so forth. This is from General Electric. Another design from Philips, when Philips used to make these scanners. This is here GSO type detector, an old type detector, again with photomultiplier tubes that are attached to the scintillating material itself. After we detect the event, we need to check to see if the energy of the event is the right energy. We do that by doing what we call pulse height analyzer. Same thing as we do in a gamma camera. We look to see at the signal intensity that comes out at the output of the photomultiplier tube. We look at that signal here and measure its amplitude. We see how high is the signal, how high is the signal here. If the signal falls between a lower energy threshold and an upper energy threshold, and we put this energy threshold here difference between, let's say, 350, 400, 450, all the way up to 650, so that we see if it is equal to 511 keV. And if it falls within that range, then we say, yes, it's the proper energy that we need to look at. So here you go. This is the lower energy threshold. This is the upper energy threshold. And as you know, we see a spectrum of energy. We do not get one particular energy. We get a spectrum of energy because the energies that come out, the signal that come out from the photomultiplier tube has jitter associated with it. Sometimes it's equal to 511 keV, sometimes it's slightly higher, sometimes it's slightly lower, but we need to accept all of these energies in order to assume that they are like 511 keV. We don't expand that window to be very, very large because otherwise we will start to acquire also scattered photons, and we really don't want scattered events into our detected events. And there are lots of scatter because, as you know, the events, a photon that is initiated inside the body will scatter inside the body, and then what comes out might be of a by far lower energy. So we really do not want to detect that photon in itself. After we assess the energy to see if it is equal to 511 keV, we need to position the event. Where did the event really occur? This is not something that we really need to do is if every detector has its own photomultiplier tube, but scanners are not built like that. We have multiple detectors associated with one photomultiplier tube. So usually we have a block here whether it's made of 8x8 or 10x10 or 13x13, depending on the manufacturer, that is coupled to multiple photomultiplier tubes. So what we do is to try to identify where did the event occur by etching the detector block like you're seeing in this case here. So if a annihilation photons come and hits this detector, the light will be generated through this whole detector all the way down. And the photomultiplier tube will see that the event is coming from this particular area, as shown in this case here. If it happens at the detector that is adjacent to it, then as the light comes down here through the detector element, towards the end, it will spread out a little bit, as you're seeing here, or more. And this spread of light helps us to identify where did the event really occur within the detector block. Because the whole idea is I want to identify, did the annihilation photon occur here, or here, or here, or here, or here, and so on and so forth. So I really need to know where did the event really occur. We also use anger logic like we do in a gamma camera. In a gamma camera, you also see the distribution of light within the photomultiplier, within the crystal, so that you can truly identify where did the event occur. So after identifying the energy of the event and try to identify the position of the event, the next thing that we really need to do is to try to assess if another event occurred at the same time, but in a detector that is diametrically opposite of the original event. That is, like I said, is known as coincidence assessment. If you think of the scanner itself, since it is like a cylinder, so it's like a circle, but there are many circles across the body of the scanner. We can think about coincidences happening within the same plane, as I am showing in here. So if this detector can be in coincidence with this detector, or this detector and that, this detector with that, this detector with that. So we talk about coincidence acceptance angle within the same plane. So that is known as the transverse plane. So this is within the same slice, there are coincidences. Each one of these detectors can be in coincidence with many other detectors. So that's within the same plane. But then there is also coincidences between one plane and the ring that is behind it. So this is along the z-axis, along the length of the scanner, along the length of the cylinder itself. And that is known as the coincidence along the axial direction, along the length of the scanner. And we know we denote that by theta, the angle theta. So it is when coincidences are within the same plane, theta is equal to 0. And then when the coincidences are across different planes, you have, one ring off, or, one detector off, it's plus or minus 1, or plus or minus 2, or plus or minus 3. So you can see these lines of response can be in all directions, correct? Because now we're going to be assessing coincidences in all different locations within the imaging volume of the scanner itself. How do we do that? When an annihilation photon happens and hits this detector, we check to see when does the time of arrival of this particular event to this detector. So as soon as the signal starts to be measured, we assess the time of arrival of that particular event. And we compare the same thing with the detector that is diametrically opposite. We also check to see when did the event occur in a diametrically opposite detector. And we check the arrival time from this side, the arrival time from that side, and we see if they arrived within the same time. They should not be exactly at the same time. There we allow a certain time jitter between them. And if the two arrived within that time frame, in this case, we are saying here 12 nanoseconds. In novel scanners, this time drops all the way down to 4 nanoseconds. Then we say that these two events occurred at the same time. This one here and that one here occurred at the same time. And obviously, there is a line that is according to this line here. Something occurred there, and that is known as the line of response in that particular case. And that is known as a coincidence event. Okay? Again, so we detect an event in this detector, we check the energy, is it equal to 511? We check the position, we check the timing and do the same thing in the one diametrically opposite, check the timing, check the energy, check the location, check the timing. And if it's all fine, then we say there is a line that occurred along that path here. And then we store that information in memory. Memory in a PET scanner is known as sinograms. And I'm showing here sinograms that are within the same plane here. You can see a line of response along this line here, a line of response along that line here, another one here. And then there are in another angle, they might be in this line or that line or that line. And you can see here when we store them in the sinogram is shown as position along the x-axis, angle along the y-axis. And each one of these locations correspond to a location of a line of response in space. So this line of response that you're seeing here would correspond to this particular location. This line of response here corresponds to this location in space. Similarly, the ones that are in green, let's say this one here is the third one, 1, 2, 3. So then this is 1, 2, 3. So it'll be this location in memory. This is for this particular slice. If we're looking at the slice behind it, then it will be for the slice behind it in this one. Or the slice behind it, the third one will be in this slice behind it, in this case, the third one. Now I'm showing you here lines of response that are parallel to each other. Parallel lines of response to each other will occupy lines at different locations, but of one specific angle. So you can see here, like this angle here is between, let's say, 2 o'clock and the 7 o'clock type location. And that would be this particular angle or this particular angle. You can see it actually by looking at one particular detector and seeing it in coincidence with many other detectors that are in the scanner. So that would occupy different angles, okay, different angles in the scanner itself. I hope this representation is clear to the audience. But that's how we store the information in the sinogram in a PET scanner. And then we take this data here, and then we reconstruct this data to generate our final image. I'm showing here a sinogram from an old scanner. Each location here, each particular pixel corresponds to a line of response in the scanner. Each one of these locations here is a slice which represent one axial position within the scanner. So slice number 1, slice number 2, slice number 3, and so on and so forth. The PET scanner is composed of multiple detectors that are arranged around the circumference of the circle, like you're seeing in this case, all around the circle. So this would be like one block of detectors, another block of detectors, another block of detectors, depending on how long is the axial extent of the scanner. So this would be like the front of the scanner, this would be the back of the scanner. And that distance here is known as the axial extent of the scanner, from the front to the back of the scanner. And like I said, we generate these slices then. So there will be a slice at the front, then the second slice, then the third slice, then the fourth slice, corresponding to one slice here, another slice there, another slice there, another slice there, and so on and so forth. This would be known as direct slices, direct sampling of the coincidence events. But you could also see that we could have from the detector and the one diametrically opposite to it. But there could be also coincidences slightly off with respect to the detector itself. So we call that a cross slice, correct? Because it's not directly in front of it, but slightly adjacent to it. So you can see that, this detector can be coincidence with the detector adjacent to it. And also this detector can be in coincidence with the detector adjacent to it. These two cross slices are not directly straight, but they are slightly shifted. And because they are slightly shifted with respect to each other, this one here and this one here, we can combine them with respect to each other and create a slice that is intermediary between the first slice and the second slice. So this way, the total number of slices, we call this cross planes, the total number of slices in the scanner will be equal to the direct slices plus the cross slices. We have a total of 2n minus 1, where n is the number of detectors in the scanner along the z-axis or along the axial direction. You can see if I remove septa from the scanner. So initially, when we used to do PET imaging in the old days, we used to acquire data in 2D mode. We would not allow lines of response that are at a large angle. So this would be stopped by the septa in here and the septa in there. But in 3D mode, we remove the septa completely and allow lines of response to be between any detector with any detector in the scanner. That is known as 3D mode, and as such, the sensitivity of the scanner, the ability to detect lines of response in any direction, is allowed. Now, of course, now the total number of lines of response that will be allowed will be n by n, so it's a very large number of lines of response. Each one of these detectors can be in coincidence with all of these detectors, and similarly, this ones can be in coincidence with all of these, and so on and so forth. This one in coincidence with all of these, and so on and so forth. So there are many, many lines of response that are allowed in the scanner. Obviously, this is allowed in 3D mode. In the old type machines, the scanners allowed you to do acquisitions in 2D mode or in 3D mode. So you press a button. This is the septa in the scanner here. This black part here is the septa that only allowed you to acquire data. So this is the septa here. You can press a button and remove that septa from the field of view, exposing the detectors that are behind the scanner, and as such, improving the sensitivity of the machine. As you acquire data in 3D mode, you will see that the sensitivity of the scanner increases. You can see here in 2D mode, it looks like this. The sensitivity is relatively very low. But as you allow more and more lines of response, you can see the sensitivity improves further, and improves a lot when you remove all of this septa. So these here, the septa are completely removed, allowing all coincidences to happen, and the sensitivity response will become triangular in shape. This is a slide showing you the difference between 3D mode. The sensitivity is much higher than it is in 2D mode. You can see the sensitivity is much lower in 2D mode versus 3D mode. And manufacturers allow you to either acquire data in 2D mode or in 3D mode or in 2.5D mode, whereby they allow you to do coincidences, not between all lines of response. So this one cannot be in coincidence with that one, but rather limit the amount of coincidences that you have. So it looks something like this, a trapezoidal shape, as you're seeing in here, a trapezoidal shape in that regard. That depends on the scanner manufacturer and how many lines of response they allow. Like I said, in the old days, most scanners used to be 2D mode. Today, most scanners are 3D mode, allowing all coincidences, with some manufacturers allowing two options, full 3D mode or a little bit less than full 3D mode, by just generating a trapezoidal type approach. Now, of course, when you remove the septa from the field of view, you will actually allow the acquisition of a lot of scattered events. So you can see here an annihilation event that is happening, and one event comes and hits this detector, and the other one will hit that detector. But in the event that the annihilation photon scatters, it will go to a different direction, and the septa will stop it from being detected in the detector itself. Whereas in 3D mode, when you remove the septa, whenever there is a scattered event, the scanner, rather than detecting an event along the red line, now will detect the event along the dashed blue line. And now the scanner will think that there is something along this line, when in reality, it should be something along that line. So in 3D mode, while the sensitivity of the scanner increases, a lot of these events end up perhaps being scattered type events that we really need to be careful about. This is here a slide to show you the extent of the amount of scatter in a PET scanner. This is here imaging a line source in air without any scatter, so no scatter in 2D mode when the septa is available. You can see there is very little scatter here. The line source is at the 0 location, so there should not be any events outside the 0 location. And the reason why you see some events in 2D mode is because the line source is encapsulated in a little bit of metal, so there is always some scatter because of that. When we put the line source in water, and that the water now appears as if like it's a scattering medium, as the annihilation events are occurring, they will scatter in the water. And now you can see that there are events that are not at the zero location, but rather outside the zero location. So the scanner is seeing as if like there are events at 10 centimeters away from the source, whether it's on the negative X direction or in the positive X direction, when in reality, there is no activity here. Here, there is no activity whatsoever. So that implies that scatter is a big issue in PET imaging. And when we change that from 2D mode to 3D mode in water, you can see that the scatter is by far larger. This is here a log scale. You can see here it goes from 0.001 to 0.001 to 0.1 to 0.1. You can see here the scatter tails of that line source is by far higher than it is in 2D mode. So when we're acquiring data in 3D mode, the amount of scatter that gets to be generated is really very high, and we really need to be careful also about it so that we can remove scatter from the acquired data. One other thing that we really need to be careful about is that when you remove septa, the lines of response that can be detected or the annihilation events that could be detected come from a very different location, and a physical location. So you can see here in 2D mode, the events are restricted to this particular envelope. No events can come from outside this envelope because the septa would stop it. Whereas in 3D mode, the events can come from any location. So if you have activity in here, which is outside the scanner, it can still be detected by the scanner. So that implies that there are lots of events that could also be detected in a 3D type scanner that should not be detected because they are coming from outside the scanner itself. And we also need to correct for that. Which brings me to the fundamental principles of PET imaging. We have always talked about an annihilation event whereby an annihilation photons hits one detector and another one hits another detector, and then we'll generate a line of response that is along this line. And we say somewhere along this line, there is a radioactive element that has decayed. And we call this as a true event. You remember I mentioned also that an annihilation event can occur and hits this detector, but then at the same time as the other annihilation event is occurring, it can scatter in the body and be detected by this particular detector. And now the scanner thinks that there is something along this dotted line rather than the original red line that it was supposed to be at. Now that's known as scattered event. This is not a good event because obviously there is no activity along the white line here. There is only activity along the red lines. So we need to get rid of this type of events at some point. And similarly, you can see that since there are so many annihilation events happening at the same time, it could be that one annihilation events occur here and an annihilation photons hits that detector, and the other one can be either stopped in the body or escapes the scanner, let's say. And at the same time, another annihilation events occur and one annihilation photons hits that detector and the other one is either stopped in the body or escapes the scanner. And because these are happening at the same time, the scanner would think that there is something that occurred along that line. And that's known as a random event. That also is an erroneous event. We don't want an event that looks like that because obviously there is nothing along the white dotted line here. It's only across the red lines that there are events. And obviously an event such as a random event should not be counted. However, the scanner is a device that just detects events. It does not know what is right and what is wrong. So the total number of events that the scanner sees is the true event, the scattered event, and the random events. That's what the total scanner sees. But it is imperative that we set the randoms to 0 and the scatter to 0 in order for us to just keep the true events in the scanner, because these are bad events here and we don't want them. And there is lots of work that is done in order to subtract scatter and subtract randoms. I will talk here about there are different ways to remove randoms from a PET scanner. There are randoms from singles techniques or delayed event subtraction. I'm not going to go into the details of that, but also for scatter, like we said, if an event scatters, rather than it being detected along the dotted line here, now it is appearing as if like it's being detected along the red dotted line. And in the sinogram, rather than the event being located in this location, it now appears at a different location, it's appearing at a different angle altogether and a different position altogether. So that is actually located in a completely different location. And when we generate the image, it is not showing me that the activity is located in the right location. So I also need to subtract that scatter. And again, there are many, many techniques for subtracting scatter. And I'm not going to get into the details of that. But scatter correction is relatively difficult to do, and it's not an easy approach. There are many other corrections that we need to do on a PET scanner. Like I said, we need to remove the randoms event. We need to remove the scattered events. There are other things that we need to correct, such as normalization, dead time. We need to correct for geometry. We also need to correct for attenuation during the image reconstruction process before we generate our final image. That would then be looking like that, whereby then the physician can go draw a region of interest and assess how much of the radiopharmaceutical that I have administered ended up being in this location, and the amount of activity or the amount of uptake that is located in this region versus that region can then be tabulated, and the physician then is able to render an opinion about the accumulation of the compound in that particular location between time point 1 or time point 2 or time point 3. But if I don't correct for all of these issues, then you can see that what is generated in this location might be completely erroneous. So I have to do all of these corrections so that I can generate an image that is truly representative of where is the activity distributed in the body. We talked about normalization. I will show you, this is here a sinogram. Now we understand what a sinogram is. Every particular location here is a line of response, but here it shows me that there are lots of line of response that seem to be more active than others. That's because these detectors seem to be performing at a slightly hyperactive than corresponding detector elements within the scanner. So I need to normalize against that difference. Usually we do a flood scan and try to see what is the difference between the different detectors, because the scanner is made out of so many different detectors, and I do not assume that they are all performing exactly similar to each other. So I will normalize against the difference. So you can see here, these detectors are more sensitive than other detectors. So I suppress their signal a little bit. So I take this, multiply it by that normalizing type signal. And now you can see a post-normalizing sinogram whereby these differences no longer exist at all. Now that tells me that all the detectors are performing exactly similar to each other. And this is here the distribution, the true distribution of the radioactivity rather than due to differences in detector response itself. That is what is known as normalization. The other thing that we need to keep in mind are issues about dead time. We know that from a gamma camera also is that these scintillators are paralyzable. As you add more and more activity in front of the detectors are not able to process the events anymore. So as activity increases, you would think that the number of events that are detected by the detector should increase and should increase in a linear manner. But the reality of the matter is that it is not the case. The detectors are paralyzable, so they go up initially, but then at some point they cannot keep up with the amount of events that are hitting the detector, and they completely stop functioning and they completely go down to zero again. So I need to correct for that. And there are ways to correct for that within the scanner. And you can see here, what we are after is to create a line that is along the dotted line here. And after correction, we could see that we generated a scan whereby on the x-axis is the amount of activity. As activity increases, the scanner performance is linear in this fashion, up to a certain extent whereby we are not able to correct beyond a certain amount. As you know, the radioactivity also decays over time. And if my acquisition is relatively a long acquisition compared to the half-life of the radioactive element, then I need to correct for that during the time that I'm acquiring the data. For example, if you are imaging O15, O15 has a half-life of 2 minutes. If your scan duration, let's say, is 4 minutes, that's 2 half-lives. So the signal that you are measuring is going to have died by 2 times, okay? Two half-lives. So that implies, 4 times, not 2 times. So that implies that the signal that you are measuring is less than what was originally there in the patient by 4 times. So you need to correct for that during the image correction, during the image reconstruction process. There is also a geometrical aspect of the lines of response, given the fact that the scanner is circular in nature. You can see the lines of response are not equally spaced out in space. You can see here the distance between this line of response and that line of response is different than the distance between this line of response and that line of response because of the angulation of the scanner. So I need to correct for that geometrically because I am putting the data into a sinogram, which is equally distanced according to from a spatial type perspective. Finally, the most important correction is attenuation correction. This is since you are detecting events that come out of the body, and we are saying this is what is inside the body, because what you are detecting is representing what is inside the body. But we know that the body itself stops a lot of signal, and I need to correct for that amount by itself. So that is known as attenuation correction. Just to give you an idea, the half value layer of soft tissue or of water at 511 keV is 7.2 centimeter. 7.2 centimeter is relatively a small distance. Perhaps it's, something like that, the 7.2 centimeter. And obviously, people are much bigger than 7.2 centimeters. So that means that if an annihilation photon is passing through a 7.2 centimeter of tissue, 50% of the signal would have completely been eliminated just because of attenuation. So that means that we need to correct for that amount that's being stopped inside the body itself. Just to give you an idea of how the images would look like if we did not correct for attenuation, on the left side is a PET image with correction for attenuation. On the right side is the image without attenuation correction. And you can see there is a big difference in the way that the images look. And obviously, we need to make that correction. Otherwise, the resultant images would not truly depicting the activity distribution in the body. What's very important about PET imaging is the fact that because we have 2 annihilation photons, 2 photons that come out from the scanner, you can see here, assuming an annihilation event occurs here, we have annihilation photons that comes and hits this detector, and the other one goes out and hits that detector. Then the probability of this detector detecting this event is equal to e to the minus mu L1. Mu is the attenuation coefficient along this path. And then the probability of this annihilation photon hitting that detector is equal to e to the minus mu L2. Mu is the attenuation coefficient along that path. But because we are not looking at only one photon, we are looking at both photons happening at the same time. So the probability of this detector detecting an event and this detector detecting an event, the 2 detectors detecting an event at the same time, is equal to the product of both of these probabilities. So if you take P1 and P2, multiply them with each other, that gives you e to the minus mu L. If you look carefully at this picture, mu L is the total distance. That means that the event, whether it happens here or here or here or here or anywhere along the L direction, it doesn't matter. The attenuation will be, the probability will be the same no matter what. So then in PET imaging, attenuation is not dependent on the location of the annihilation event, but rather on the path length of the annihilation photons inside the body. It's a very, very important concept that is fundamentally different than it is in a gamma camera. In a gamma camera, because we have one photon that is being detected by the scanner, the amount of attenuation is directly dependent on the depth of where the radioactive atom is located. In PET imaging, it is not dependent on where the radioactive atom is located. It is dependent on the path length along which the two annihilation photons travel throughout the body. And that concept has been leveraged in order to correct for PET imaging. And that's the whole reason why really, truly, initially, PET imaging really became a very important modality, because we could correct for attenuation in PET, whereas we could not correct for attenuation in SPECT imaging, in just through PET scanners and through gamma camera images. So we corrected for the attenuation coefficient because we knew what is the path length inside the patient. And we used to do that in multiple techniques. We used to rotate a source around the patient and try to identify how much the attenuation is and generate the resultant type images. So we would show you, if you rotated a source around the patient, you would generate an image that looks like a CT image. Correct? Because that's what a CT scan is. You rotate a source of X-rays around the patient and you generate an image. Very similar to that, we rotate a source around the patient. This source is 511 keV, and we generate an image that is an attenuation image that looks like a CT scan. And we use that to correct for the attenuation that is inside the body. And we would generate these images. This is the standard emission images, the annihilation photons that are coming out of the body. This is the attenuation image. We would call that transmission image by rotating a source around the body. Then we use this image to correct that image, the top image. So we use the transmission image to correct the emission image and generate the final image that you're seeing at the bottom there. And you can see with the attenuation correction, the transmission correction, we can see now much clearly the activity distribution inside the patient. We can then easily identify regions of interest and try to see what is the activity distributions in these particular locations. With the advent of PET-CT, since now we can do a CT scan in order to create these attenuation maps, we acquired the CT scan and we use the CT scan to correct the emission data. So rather than do a source that rotates around the patient with a PET-CT scanner, we replace that type of an image with a CT image itself. And we correct the CT scan. We use the CT scan to correct the PET data and generate here on the right side the corrected PET scan. In addition, we can take this image, the corrected PET image, and superimpose it on top of the CT image to create these really very nice fused images, whereby we can easily now identify areas of malignancies or areas of suspicion of malignancies much more clearer than it was in the PET-only image. And it is because of this superimposition of the PET scans that are corrected for attenuation on top of the CT scans that these images became really very, very helpful for the interpreting physicians so that they can manage their patients by far more accurately and by far more effectively. One thing, however, that we need to keep in mind is that these CT images are acquired at a different energy than the PET image. As you know, the PET images are acquired at 511 keV. These CT images are acquired at a kVp. The peak energy is usually 110 or 140, and that means that the effective energy is perhaps maybe 70 keV. So we cannot take this CT image and use it directly to correct the PET image because these are at two different energies. And we do know that attenuation coefficients change with energy, as you can see here on this slide. As energy increases, attenuation coefficients here decrease, obviously, because as the X-ray energies or the gamma ray energy or the annihilation photon energy increases, it can penetrate through the body relatively very easily, and the attenuation coefficients would drop. So you cannot take a CT image and directly use it to correct for the PET image. We need to transform the CT image to a PET image attenuation coefficient before we correct for that. And there are clever ways of doing this. The way that it is done in PET scanners is known as the bilinear transformation. We take CT numbers that are acquired at 140 or 120 kVp and transform those to 511 keV attenuation coefficient using this bilinear transformation. So if you have a CT number of, let's say, minus 100, then you go up the curve and then you transform it into so-and-so attenuation coefficient at 511 keV. So then that means that we take these CT images on a pixel by pixel basis, see what is the CT value, CT number, CT Hounsfield value, and then transform that into its corresponding attenuation coefficient at 511 keV, and then use the resultant image to correct the corresponding PET image. And I will show you that in this case. This is the original CT that is acquired. This is its corresponding attenuation coefficient at 511 keV. And you can see these images now that are used to correct the PET data are by far more superior to what we used to generate from the source that used to rotate around the patient in the old days. It used to take us so much time to do so. These images are then used to correct the PET data and generate our final image. One last correction that we need to do is the calibration, which is the efficiency of the scanner. The scanner only counts events. You know, anytime an annihilation photon passes the energy test, the timing test, and the location, and so on and so forth, I put it into memory, and I would say, okay, this is one event, another event, another event. So I have so many counts per unit time. I need to transform that into activity concentration. That is known as the calibration of the scanner. That is known as the efficiency of the scanner, which is transforming counts per second to activity concentration. And the units is counts per second per microcurie per cc or vice versa. These units are then transformed into another scale that is used by the physicians to read these PET images known as SUV. And the SUV is actually the activity concentration that we get after the scanner calibration. At any particular pixel location, the pixel value would be in activity concentration. Then you divide that value by the amount of administered activity into the patient, and you normalize it by a normalizing factor. In this case, we are using the patient weight in this case. The patient weight can be in kilograms, so this would be SUV based on body weight, or SUV based on lean body mass or body surface area and what have you. These are the ways that you need to do to correct all your PET data before you generate your final image. I'm going to speak shortly about, I see that the time has passed so quickly. I see that, you know, there are several factors that affect your PET image resolution. As you can see here, there are many, many factors that are here. I'm going to go over them relatively very quickly. The detector size is very important to determine the image resolution. If the detector size is large, then your image resolution is going to be relatively low. And usually the resolution of the scanner is approximately equal to the detector size divided by 2, so half of the detector size. There is also an issue related to depth of interaction. You can see here if I have an annihilation event that hits the detector head on versus if the annihilation events occur to the edge of the scanner, because the detector is tilted a little bit, it will pass through the detector. So we call that penetration or depth of interaction. And that would cause the annihilation to photon or the line of response to be located in a different location. So that directly implies that your resolution of the PET image is not uniform across the picture. The resolution of a PET image changes from the center of the image to the edge of the image because resolution drops as we go to the edge of the field of view. We also need to know that the energy of the positron as it's emitted from the nucleus is different for different radionuclides. And because of that, the annihilation, the positron has a certain distance before it annihilates. So the location of the lines of response is not exactly coincident with the location of the radioactive atom. And that places a certain discrepancy between where you're measuring the signal from where really the radioactive atom is. That's known as positron range. And like I said, different radioactive elements have different energies, and the different energies result in different locations of where you are identifying the lines of response. Also, there is a difference in the what we call a collinearity, non-collinearity effect. The annihilation photons that get to be generated, the positron itself, might annihilate with an electron before it loses all of its energy. So it still has some momentum associated with it. And because of that, the two annihilation photons that gets to be generated might not be equal to 180 degrees back to back, like it should be along the red line. Sometimes it is emitted at slightly different angles because it still has some momentum associated with it. And because of that, that causes loss of location of the annihilation of the line of response. So you can see here, rather than it being along the red line, it can be detected along the dotted line here, or it can be detected along the dotted line there. Also, the image matrix size that you are using when you're reconstructing your image, are you reconstructing it at 64 by 64, 128 by 128, 256 by 256? That also causes differences in image resolution in your resultant images. The filter that you are putting in your final image also has impact on your final image. You can see here, this is a PET image without filtering. This is with 6mm filtering, 12mm filtering. You can see the images gets to be blurred. And as such, the activity distribution gets to be changed slightly between the image that is on the left versus the image that is on the right. So if the person is trying to identify how much activity is in this region, the value that you are seeing on the left side will be different than the value that you're seeing on the right side. And we talked about, the image reconstruction type techniques. There are new techniques with OSEM reconstruction versus filter back projection type reconstruction. Most of scanners these days utilize OSEM type reconstructions. I'm going to talk a little bit about sensitivity of the scanner. We talked about 3D versus 2D, and we said that 3D are more sensitive. However, we have lots of scatter, so we need to be careful about scatter. You can also increase the sensitivity of the scanner by making the scanner much longer to cover the whole patient, or you can make the bore size of the scanner much narrower so that you can detect all of the lines of response that are being emitted from the scanner. Now, obviously, the best design of a scanner is to make it a sphere, and you ask the patient to go inside a sphere, but obviously that is very claustrophobic and there are no such system. But you can make the cylinder to be very, very long so that you can cover the whole patients and cover all lines of response that are being emitted. In any case, after you correct all of these corrections that I have mentioned, then you create your final image, then you can draw your regions of interest, generate your outcome measures, and then manage your patients accordingly. And as I said, right now, it's only PET-CT scanners that are out there. There are no PET-only machines. These are relatively old slides, but this is a scanner from General Electric, from Siemens, as well as from Philips. They used to have a scanner called the Gemini. Philips is no longer in the business now. There is another company called United. My understanding is that there is another company in Europe that also generates PET-CT scanners that is also out there. But again, in the old days, we used to generate PET-only machines. Now we are generating PET-CT scanners whereby you get the PET scan and you get the CT scan. We overlay these two images on top of each other, and you get to see these really very, very nice, very powerful images for the physicians to be able to manage their respective patients. I'm going to stop here and perhaps maybe take a few minutes I don't know if we have questions to answer, but I'm gonna stop here and see if anybody has a question. In your point of view, what is recommended? A PET-CT with good material detector or a good PET-CT that improve the image reconstruction with a good software? Well, what we need is both. We need a PET-CT scanner that has a very good detector, and these days the good detectors are BGO as well as LYSO. I will describe the difference really between LSO and BGO in the next presentation, because there are capabilities of what we call time of flight imaging in PET scanners. BGO detectors cannot do time of flight because of the detector characteristics itself. We also need to have very good image reconstruction type techniques, because if you acquire very good data, but then you cannot reconstruct it very well, then it's useless still, correct? You cannot generate a good quality image if you don't have a good reconstruction. So both of these are very important. If you're asking me, should we get a PET-CT scanner or a PET-only scanner? That is a very easy question to answer, and I would say you should definitely go with a PET-CT scanner, because as I had mentioned, the CT gives you the anatomical landmarking that you can use in order then to see clearly where is the distribution of the pharmaceutical that you are looking at, that will then help the physician to better manage the patient. Plus, a PET-CT scanner is a much quicker acquisition in order to acquire the attenuation scan. Like I said, you need a CT to correct for attenuation. If you don't have a CT, you need to rotate a source around the patient or correct for attenuation type approaches. In the day of artificial intelligence, believe it or not, we are able to generate a quote-unquote fake attenuation map based on the emission PET data and eliminate the need to correct for attenuation by using that fake attenuation map. Lots of work being done in that domain, and people are wondering whether we really need to acquire a CT for PET imaging, since that would increase a little bit of radiation exposure. If we can replace that by an artificial intelligence attenuation map that does not impact the outcome, then perhaps maybe that's the better approach. Plus, also the scanner will be much cheaper because you don't need to have a CT scanner altogether.
Professor, we have a question on a Q&A application. Which is the best scintillation crystal to receive 2 photons? Can a good scintillation crystal solve a good image reconstruction?
Yeah, so again, I mean, relatively very similar to the previous question. Right now, there are 2 primary detectors or scintillators that are being used in PET imaging: LSO or LYSO, and then BGO. And the reason why these are the 2 detectors is because the BGO have a high stopping power, so it can detect all the signal. There are no annihilation photons that pass through the detector without any detection, and it's relatively cheap. However, the problem with it is that the amount of light that it generates is relatively little compared to LYSO. The amount of light that LYSO generates is much higher, and because of that, the signal has less jitter in it. So we are able to identify whether it's 511 keV more accurately rather than it is BGO when we are using LSO. The problem, however, is that it is relatively more expensive to have a PET scanner made out of LSO rather than BGO. And that's why, different manufacturers use different type detectors and try to sell this product versus that product. It is like you are saying, what is a better car? Shall I buy a Mercedes, or shall I buy an Audi, or shall I buy a BMW? Both are very good cars. Both are really very good. There are differences in one car versus the other car, but both can give you what you really want.
Thank you, Professor. Maybe it's better to move on to the next talk. And the next talk will be about quality assurance testing and quantification related with PET imaging.
So quantification in PET imaging. Again, no disclosure. So I showed you this slide before, and I said that one of the most important components in PET imaging now is we put this PET image on this CT image, and we generate these fuse type images. And one of the most important component of PET imaging is that now the physician can go and interrogate every particular pixel location and determine how much of the radiopharmaceutical that is injected in the patient, and identify, what is its intensity. Is there so much compound that went there or less? And usually, depending on the compound, let's say we're talking about fluorodeoxyglucose, as you see here in this case, FDG, FDG is indicative, accumulation of FDG in tissue is indicative of cancer. So that directly implies that if there is more and more dark spots, then that is suspicious of more and more these areas being cancerous. Now, of course, we know that the brain is obviously processing lots of signals and stuff like that. So that's why also FDGs goes to the brain. So we really don't use FDG to evaluate the brain. But if you have lots of FDG in the lungs or FDG in the lymph node, then that directly implies that there is a high probability or suspicion that there is potentially cancer cells in these locations. So that means that the physician is relying very heavily on the fact that the values that I am getting in here are accurate and are quantifiable. So, it's truly representative of that physiological state. So we really need to make sure that the results truly represent the outcome here. Let's go to the idea of SUV again. I mentioned that it is the activity concentration in that location divided by the injected activity and normalized by some normalizing factor. So if you look carefully, it's activity concentration in the numerator versus activity concentration in the denominator. Assuming you use a specific gravity of 1, patient weight is in grams, or you can make it in cc's, with a value of 1 as far as gram to cc's for water. So a ratio of concentration in the numerator versus the denominator. So then I'm going to do this particular small quiz for you. So if you have a patient, let's say weighing 1 kilogram, and you inject this patient with 1 millicurie of activity, I'm saying that the SUV is 1. Now, if I do the same thing, but now the patient is, let's say, 10 kilogram, and I inject that patient with 1 millicuries, what will be the SUV? If you said that the SUV is 1, you are correct. If you said that the SUV is 0.1, you are wrong. And the reason being, it's a ratio of concentration. It is this activity distributed in this volume, correct? And that's what we're saying. It is this concentration divided by the activity injected, normalized by the patient weight. Similarly, if I look at the following scenario, whereby I inject a patient with 1 millicurie and they are 1 kilogram, I get an SUV of 1. And now, if I do the same thing, but rather than injecting them with 1 millicurie, I inject them with 2 millicurie, but the patient is still 1 kilogram, what would be the SUV? If you said that the SUV is 1, you are correct. If you said that the SUV is 2, you are wrong. Again, it's a ratio of concentration. It is this activity divided in this volume, which is the activity concentration, normalized by the injected activity and the patient weight. If the activity is uniformly distributed, then it is always equal to 1. The SUV is always equal to 1. There are several factors that modulate the accuracy of the SUV in a patient whenever we are imaging a patient. Particularly for, let's say, FDG type imaging. We talk about patient compliance issues. Whenever you're doing FDG imaging, the patient needs to fast. The patient glucose blood levels needs to be within a specific range. Otherwise, these two factors would modulate the distribution of the activity inside the patient. Because we're assuming that when you inject this activity, it's going to uniformly distribute inside the body. And it's only these areas that are behaving abnormally that's going to pick up more of the activity inside the patient. Now, there are other factors that modulate the distribution of the activity in the patient. So let's talk about the certain scan condition. It has been clearly shown that the activity, as it distributes in the body, it reaches a certain plateau. So it increases to reach a certain plateau. But then if you wait a long period of time, then it will wash out of the areas of interest. So that implies that the time that you image is critical. Because if you image the patient, let's say at 60 minutes versus 120 minutes versus 180 minutes versus, let's say, 20 minutes, you will have different SUVs. So it's very, very important if you are imaging a patient that you always image the patient at the same time during repeat imaging times in order to eliminate the effect of the time on the activity distribution inside the body. Here it shows you the activity at 45 minutes, 82 minutes, 315 minutes. If you assay the amount of activity in the different pixel in the region of interest, you will see that they will be different. And that's very important for us to consistently image patients like at about 1 hour. That's why the protocol always is to administer the activity, wait 1 hour, and then image the patient within an hour after you administer the activity. It's also very important that when you administer the activity, you don't infiltrate the patient. If you infiltrate the patient, lots of the activity will stay in the arm rather than it being distributed inside the patient. And that will impact the amount of uptake in the various regions in the patient. And then you will have different activity concentrations and SUVs accordingly. Because if you infiltrate the activity in the arm, then the amount of injected dose that is delivered to the patient will be different than what you are anticipating it was, because most of it ended up being in the arm rather than it being distributed inside the patient. Similarly, when you are entering, in order to calculate the SUV, you need to enter the weight of the patient. You need to put the unit of the patient's weight, whether, here in the United States, we still use pound rather than use the Système International, using kilograms. If you used megabecquerel or you used millicuries, also it will impact the result. What time did you inject the patient? Also, all of these factors will result in different SUVs of a lesion of interest that you have. So you need to be very, very careful in quantifying the results so that you can accurately represent what is the extent of malignancy that this patient has. Another component is motion. We have said that we use the CT and the PET data. The CT is used to correct the PET data for attenuation. So if the patient moved between the time that I'm acquiring the CT versus the time that I'm acquiring the PET, then the CT cannot be accurately used to correct the PET data for attenuation purposes, and that would modulate the distribution of activity inside the patient. So we really need to be very careful. The patient did not move between the PET and the CT scan. There are certain motions, however, that are non-voluntary. You can see here if the patient is breathing and the breathing cycle is shown in this blue line, usually the CT scan is acquired under one particular part of the breathing cycle because CT is very fast. Whereas PET takes many cycles, it's a very long scan and it is acquired over many breathing cycles. So there is a mismatch between the PET and the CT scan. And you can see here, the CT was acquired at, like relatively end inspiration here, whereby the lungs are fully inflated, whereas the PET was acquired over a quiescent period of the patient breathing cycle, so the average breathing cycle. And that means that this part of the lung here, which has very little attenuation because it's made out of air, is used to correct the PET data. And that means that this part is not properly corrected. So it appears as if like it's a photopenic area, as if like there is no activity in this location, which is not true. If you have a lesion in this case, like you see in this situation, that will be impacted accordingly and will be underestimated. Similarly, you can see here the tumor on the CT image. There is no tumor at the corresponding PET image because these are not aligned with respect to each other. And as such, when you're using the CT to correct the PET data, there will be an artifact in the image accordingly. You can see it here, the tumor on the PET, not located on the CT, and so on and so forth. You can see for cardiac imaging, you can see the PET image of the heart is outside the CT silhouette of the heart also. So the CT and the PET are not properly matched to do proper attenuation corrections. There are multiple ways to correct for that. I am not going to specifically talk about it, but I can show you after we correct for this difference. You can see here the lesion that I was talking about that has relatively low activity concentration. Now you can see it much clearer. And also this photopenic area has been corrected. And the SUV changed for this lesion by 57%. So it changed dramatically because of this mismatch. And after we have corrected for this mismatch. This here situation whereby you can see the PET heart the heart on the PET image is outside the location of the CT image. We could correct for that, and now it is really nicely aligned accordingly. Whereas before, there used to appear as if like there is an infarct here on the left side in panel C. This is now corrected for in panel D, and you don't have that that artifact anymore, just because of this motion and because the attenuation correction was not properly applied. There is also the fact that when you are acquiring PET data, the patient is breathing during that time. So if you take a sphere, let's say, and the sphere should look like a sphere during the time that the PET data is acquired. But in reality, because the PET data is acquired during the whole time of the patient breathing, a spherical shape will appear as an oblong shape like these. And since SUV implies the activity concentration, the volume now of the object is much bigger because it's now oblong rather than spherical. So then the activity concentration will be underestimated. And you can see here, the activity is very nicely circumscribed within the sphere, and now it is spread out. So the activity concentration is underestimated. And as such, the SUV will be underestimated accordingly. And because of that, there will be an artifact, and you are not truly reading what is the amount of accumulation of the compound in that particular lesion. So there is need to be a correction for that. And again, there are multiple techniques to correct for that. You can see here the lesion at the dome of the liver before correction and after correction. Now you can see here the correction technique that was applied is a correction that causes the whole image to be noisy, but at least that lesion is much clearer to visualize compared to the previous type image. And I'm showing it to you here more accurately, whereby you can see the lesion spread out here because of the patient breathing cycle. The SUV in this lesion was 5. And now when we correct for that particular motion, you can see now the lesion much clearer and much more circumscribed, and the SUV is much higher. The correction technique allows us to actually display the lesion as it's moving up and down during the breathing cycle of the patient by us acquiring multiple pictures at a much faster rate. And you can see it here, going up and down accordingly. And that can be used for multiple other purposes, for primarily radiation treatment planning purposes. The fact that we are using the CT to correct the PET data introduces several also artifacts for PET CT. One of the artifacts that I want you to be aware of is that we inject contrast usually in CT scanning to improve the appearance of the CT images. Injecting contrast into a patient to improve the quality of the CT also increases the CT Hounsfield unit where the contrast is located. So physically speaking, whenever the CT was supposed to show tissue that has a CT number of, let's say, 400, the corresponding attenuation coefficient was supposed to be this value over here that is shown. Whereas with contrast, the CT number now artifactually increases, thereby increasing artifactually the corresponding attenuation coefficient, when in reality it shouldn't. The attenuation coefficient of soft tissue should stay the same at 511 keV, whether you have contrast or you don't have contrast. So we really need to be careful whenever we inject contrast into a patient to do that correction. That is here a slide to further elucidate this. You can see here CT scans without contrast. It's very easy to separate bone from soft tissue by just window and leveling against certain CT number values, because we know bone is a much tougher material, so you can easily see it by saying set the window and level in such a way that you only see bone and remove soft tissue. But when you have contrast, as we're seeing on the panel on the right, the contrast is in the heart here, then you can see it's very difficult to separate bone from soft tissue that is with contrast. So the scanner would think that this area is bone, and as such would correct these areas as if like they are bone, when in reality they are soft tissue. And as such, you will have artifacts accordingly. There are ways to correct for that by using techniques whereby you can change the correction coefficients from regular CTs to CTs with contrast available on board, whether the contrast is intravenous contrast or the contrast is oral contrast accordingly. Another artifact that is there is due to the fact that the CT field of view is 50 centimeter, whereas the PET field of view is 70 centimeters. So the CT field of view is shown by the red dotted line here, whereas the PET field of view is shown by the blue magenta line here. And there is a discrepancy between the CT field of view and the PET field of view. That means that the CT image would only show a certain part of the patient, but rather not all the patients. So an example is this case. You can see here a patient that's scanned with arms down, melanoma type patient. You can see the arms are truncated in this case because the CT cannot go beyond a certain amount, beyond the 50 centimeter diameter. Whereas the PET field of view is 70 centimeter because we have always imaged PET people with arms down, so that field of view of a PET scanner has always been wide enough so that you can image the whole patient. The CTs, however, have always been done when you image the patients with arms up so that you reduce the amount of beam hardening, because there is lots of bone in the arms, so that you would have better image quality if you image the patients up whenever you're looking at the chest, abdomen, and pelvis region. However, this discrepancy means that this PET image, since you are using the CT to correct the PET image, there is no data at this location to correct the PET data. And if you have lesions in the arm, as in this case, and this is a melanoma type patient, then this lesion will not be properly corrected. There are techniques to correct for that. And this here slide shows you the images before correction versus after correction. And you can see the SUV changed immensely before correction to after corrections accordingly. So we need to also be careful. And that's an issue of quantification. When you are looking at lesions that are beyond 50 centimeter, you need to make sure that the CT is corrected in such a way that it has the ability to correct beyond the 50 centimeter axial extent. And like I said, there are ways to do that on the PET CT scanners themselves. Other type issues that are on the that affect the quantification of a PET scanner fall under the scanner performance itself. Okay, so let's talk about that component from a physics perspective. We talked about the fact that if there is an annihilation photon, annihilation event, then there will be an annihilation photon that will be detected in the detector and another one in that detector. So the scanner is made out of thousands and thousands of detectors. This is a relatively short axial extent scanner, about 15 centimeter axial extent from the front to the back, but still can be made of many, many, many detector elements. And we are assuming that all of these detectors are performing well and everything is working very well with them. That's why we perform daily QC in the morning just to make sure that everything is okay. And I will talk a little bit about quality control of a PET scanner later on in the presentation. And you can see if all the detectors are working fine. This is a phantom here. This is an IEC phantom, uniform background, 6 spheres of different diameters, all filled with the same amount of radioactivity concentration, but at a different concentration than the background. And all the detectors are performing well. This is a sinogram of this particular phantom. This is the raw data. This is the reconstructed data on the left side. So each pixel here corresponds a line of response, and the intensity corresponds to how many lines of response were detected in that particular location. And you can see here, if all the detectors are operating properly and everything is uniformly normalized, you can see that this would look very nicely, depicting that all lines of response, all detectors are functioning properly. But if there are some detectors that are bad, then you will see bands like this in the scanner. And if there are a small number of detectors that are bad, perhaps you cannot see this visually on the scan between this image and this image. They really look the same, more or less. However, if you go and quantify the values in the different locations, they will vary slightly because these detectors are not functioning. Now, if I exaggerate this effort by making more and more detectors that are not working, you can see this effects more clearly in the resultant reconstructed image. If we look at the quantification for the different spheres, so the different plots are the different spheres. You remember I said there are 6 spheres here. The largest sphere is the blue line. The smallest sphere is this like brown line. And here on the x-axis showing the number of detectors that are going bad. And we look at detectors from blocks in this case. So you can see here, based to the normalized to a baseline whereby everything was working properly, how much do the activity concentration or the SUV percent difference varies depending on the number of detectors that are going bad. So, we really need to be very careful. So here you can see this is a difference of about, 35% difference. This one here is showing a difference of like about 22% difference, and so on and so forth. So we really need to be careful about that. So by just having detectors that are not working, you can have on the patient a difference of about 20, 15, 10, 30%, depending on the number of detectors that are not performing. So that directly implies if the physicians did not know about this, that their SUV measurement of that patient might show a difference of 20 or 30%, and it'll show lower by 20 to 30%. And that means as if like the treatment that the patient is having is actually working, when in reality, it's not true. It's just that the scanner had bad detectors, and the SUV that the physician is reading is artifactually low because of that fact. So we really need to be very careful about quantification. This is here effect of normalization. You remember I told you that the uniformity of the detectors should all be the same. If the uniformity is bad, I have induced a bad uniformity here, and I use this uniform image, this bad uniform image, to reconstruct my data. And this artifactually placed bad locations in the final image. You remember the PET images are acquired in chunks in this case. So this appears in the top chunk, and the middle chunk, and the lower chunk, and in the extreme lower chunk, showing that as if like there are lesions in this reconstructed image, but in reality, it's just because it's the wrong normalization scan. It had an artifact in the image. And we really need to be careful about that. Otherwise, the physician might think that the patient has a tumor in here, when in reality, there is no such tumor. And showing an SUV that is actually relatively high compared to normal tissue in this location. Whenever we do PET imaging, as you know, we assay a dose in a dose calibrator. We say what is the injected dose. We measure the activity, and that would be the amount that we say this is how much we're going to be injecting the patient. So if the dose calibrator is not working properly because there is some variability, or it's not working fine, or it has a bad dose calibrator, that directly implies that what I am administering the patient with is not accurate. And that directly translates into the measurement of the SUV value whenever I am assaying this lesion or that lesion, because the SUV number depends on the value that comes up from the dose calibrator. We did a study in order for us to see what is the variability in dose calibrator between different centers that we have. And we can expect about 5% variability, but then you can see some dose calibrators exceed 10%. This is in one direction, and there are other dose calibrators that exceeded in the other direction. So we really need to say that if you imaged your patient day 1 using this dose calibrator, and then day 2 using this dose calibrator, just the fact that the dose calibrators were different by about 20%, this is plus 10%, this is minus 10%. So the difference between dose calibrator day 1 and day 2 is 20% just assaying the dose. So rather than saying I am injecting the patient with, let's say, 10 millicuries, now you're saying the patient is being injected with 8 or 12 millicuries. That affects your SUV value accordingly. So it's very, very important, other than taking care of the scanner itself, that you need to also take care of the ancillary equipment that we use with the PET scanner, such as the dose calibrator. A very important component is the limited resolution of the PET scanner itself. This is known as partial volume effects. As we have said, the resolution of a PET scanner these days is in the range of about, the image resolution is in the range of about 5 to 8 millimeters. This is an old slide, between 7 to 12 millimeter, depending on the scanner that you buy. Newer scanners have very small crystals, and because of that, the resolution gets to be better and better. But usually, most current commercial clinical PET scanners have image resolutions that are in the range of about 4 to 8 millimeters in this regard. That means that if you are imaging an object that is in that range, about 4, 5 millimeters, then that means that the scanner will have a difficulty in seeing that object and seeing the activity concentration in that particular object. That is known as partial volume effects. Usually in anatomical imaging, such as CT, X-ray imaging, such as mammo, fluoro, the resolution is relatively very high, and the partial volume effects are not perceived visually by the eye. But in PET scanners, and in gamma cameras, since the resolution is relatively on the order of several millimeters, approaching a centimeter in certain old type machines, then that is perceived by the eyes. We can easily see a millimeter or 2 or 3. So when the resolution is several millimeters, we can easily see it visually. And that causes what we are seeing, a partial volume. This phenomenon occurs also in CT scanners and in MR scanners, but to a much lesser extent, because the resolution of these machines is much higher. Like I said, in a CT scanner, the resolution is in the order of sub-millimeter, whereas in a PET scanner, the resolution is on the order of several millimeters. So if we are looking at the image, and this is its pixels, and if there is a lesion that's smaller than the pixel size, then obviously the lesion is going to spread out into the resultant image, and the SUV that was originally assumed equal to SUV1 will be originally much higher than the measured SUV. To show you this more visibly, this is a JZAC type phantom. These spheres are of different diameters, but they are all filled with the same activity concentration, the same amount, okay? Activity concentration. So I make a solution, I add the same amount of activity, I put a certain amount of activity in that solution, so it is certain amount of activity concentration. Then I fill these spheres that are of different diameter from the same activity concentration. And then I image this in a PET scanner. And when you look at the image, you visually perceive as if like this bigger sphere has more activity than this small sphere. And when I measure it, it also shows that the largest sphere has more activity than the smallest sphere. That is known as partial volume effect. So if I'm looking at it from a tumor in a patient, if the tumor in the patient was this size, then the activity concentration might appear as such. And then let's say that the tumor shrunk in size after treatment or whatever, but it still had the same activity concentration as before. The image, however, the resultant image will not show me the original activity concentration, will show me a reduced activity concentration. So that affects the quantification of the resultant PET image. So we really need to tell our physicians very clearly that if you are imaging a patient and you're looking at tumors that are relatively very small, when you are interrogating these tumors to see what is the SUV or what's the activity concentration in that lesion, you need to be aware that the value that you are reading is underestimated because of partial volume effects. So that's an important component that we need to tell our physicians about. We will talk about time of flight later in advances of PET imaging, but that imaging technique also impacts the SUV that you measure from the resultant PET image. When you use time of flight imaging versus non-time of flight imaging, you can see here a tumor that the SUV value without time of flight is reading 2, whereas the SUV with a time of flight imaging is reading 3. It's the same patient, it's the same image, but one processed with time of flight technique one without time of flight technique. And because of that, I can see different activity concentration or different SUV values. So it's very important, again, that whenever you're imaging a patient at different time points, as you are managing the patients, treating the patient, and trying to do PET imaging to see how they are performing, it's very important that if you process the image the first time with time of flight, then the next time you should process it with time of flight. Otherwise, just time of flight imaging would impact the SUV measurements by itself. If you replaced your PET CT scanner from time point 1 to time point 2, and now you have the capability of time of flight type imaging, then looking at the previous image that was done without time of flight versus the time of flight image will impact the outcome of the quantification. To further, elucidate what does time of flight imaging mean, you remember I said that if there is an annihilation event that occurs, there will be an annihilation photon that will hit the detector and another one that will hit the diametrically opposite detector. And then the line of response will be between these two detectors. I don't know where did the event occur along the line of response. All what I know is it occurred somewhere along this line, but I don't know where exactly. That's the conventional way, or non-time of flight imaging. In time of flight imaging, we record the time of arrival. We take into consideration also the time by which the annihilation photon hits this detector versus the annihilation photon hitting that detector. And it is that time difference between this detector detecting the event and this detector detecting the event that can help me identify more accurately where along this line did the annihilation photon really occur. That means that this detector should process the signal very quickly. And similarly, this detector should process the event very quickly. And that's why we call them time of flight type imaging. That means that the crystal, the scintillator in this detector, needs to have the ability to process these events very quickly compared to other type scintillator. And that's why in the previous question that was raised, what detector should I use and what detector should I not use, and so on and so forth. If you are interested in doing time of flight imaging, you need to make sure that the detector that you have is capable of time of flight. Right now, the detectors, the scintillators that have time of flight capabilities are LSO or LYSO, whereas BGO cannot do time of flight type imaging. Also, when we reconstruct the PET data, you remember I said that the resolution of the PET image changes as you go from the center of the image to the edge of the image. That change in resolution can also be corrected for by what we call point spread function type reconstruction. We're correcting for the change in image resolution within the field of view of the scanner. However, when you do that, that implies that there is going to be a change in the activity concentration in the various pixels, because before, when the resolution was lower, there is more partial voluming in that particular area of the image compared to the center of the image. Also, the correction technique itself introduces some error. We call that Gibbs artifact. I am not going to get into the details of that, but it causes what we call ringing artifact. Sometimes it causes an overestimation of the activity concentration. So on the left side here, you see a PET image of a lesion without PSF reconstruction, point spread function reconstruction, or resolution recovery reconstruction. On the right side with, and obviously it is with ringing, that means it is with this artifact, the Gibbs artifact, because the change is really huge from 8 to 16. Again, this is an issue that's very important whenever we talk about quantitation. And this is here the slide to show you that the resolution changes from the center of the field of view to the edge of the field of view. So it's very important. This is here a slide that shows you standard image reconstruction in the old days. On the left side, in the middle panel, standard image reconstruction with resolution recovery, meaning with point spread function type reconstruction. And on the right side, it is with resolution recovery as well as time of flight imaging. And when we look at 3 different regions of interest, areas that we are interested in, you can see that the SUV is different for these 3 regions from the left panel middle panel to the right panel. And all what I am doing here is the same PET data that was acquired. I am reconstructing it with different processing technique. One is with time of flight, and the other one is with PSF. And you can see SUVs changing from 3.1 to 5.6, 1.8 to 3.7. And this would change the management of the patient, because that tells the physician that, okay, the lesions is not really performing as I would have expected them to perform from this therapy or that therapy. So we really need to be very careful as to how we process our images from time point 1 to time point 2. The last thing I wanted to cover on quantification is also the image reconstruction technique that is used. Most of the time we use now what we call iterative reconstruction techniques. You can see here we vary the number of iterations and the number of subsets to generate our final image. In this case, the left panel is with 2 iterations, middle panel is with 4 iterations, right panel is 6 iteration, and we're drawing a region of interest on the on a tumor that's in the lung, and you can see the SUV changes from 3.1 to 4.7 to 6.3, just changing the number of iterations, one of the parameters for the OSEM reconstruction. Similarly, if you keep the same number of iterations but vary the number of subsets, the number of updates, basically, you can see here 8 subsets, 14 subsets, 21 subsets, changes from 4.7, 6.6, 6.8. Again, need to be very careful about how you process your images. Similarly, when I have said that before, when you are changing your filter, changing from no filter to 6 millimeter filter to 12 millimeter filter, the SUV also changes accordingly in this case. When you are also acquiring the PET data for a short time will create images that are relatively noisy compared to images that are less noisy if you acquire for longer duration. And images that are noisy will create artifacts in measuring the SUV, particularly because we measure the SUV max, which is the maximum pixel value in a region of interest. So if the image is noisy, there is more propensity that the SUV value that you are reading might be artifactually high because of noise in the image compared to an image that is less noisy. So again, the scan duration is also an issue. And we have talked about the matrix size being also an important factor determining the quantitation in the image. There are also techniques that are being recently utilized about a reconstruction algorithm that uses regularization in order to suppress the noise. You can acquire data with relatively short duration, but use regularization so that you suppress the noise that is in the image. You can see on the left side, the image is relatively noisy compared to the image that is on the right. You can see noisier meaning there is lots of, like salt and pepper, it's like a pixelated type image compared to the image that's on the right. And because the image here is noisy, the maximum SUVs that you see on the left panel is higher than the image that's on the right panel. This image is not filtered. It is regularized during the image reconstruction. So we are not applying a filter across the whole image. We are saying during image reconstruction, do not generate results that are relatively noisy with respect to each other, meaning that pixels that are adjacent to each other should not show large variability in pixel values. I'm going to end this presentation by talking about quality control on a PET scanner in order to suppress these changes due to the scanner performance. So there are daily checks, there are weekly checks, there are quarterly checks, and there are annual tests that we need to do. The daily checks, this is from a General Electric type scanner, looks at the scanner. So the scanner, like I said, is a cylinder. We cut the top part, we open it, and we show it to you like that. So this is the front of the scanner, this is the back of the scanner, and showing here all the different detectors that are in the machine. Each pixel here represents a detector element, and we're looking at the coincidences, we're looking at singles, we're looking at dead time, we're looking at the timing of these detector elements, and so on and so forth. When you perform this test, you have to put a source of activity inside the scanner. In the old days, the source of activity was embedded in the scanner. You press a button, the source is extended and will rotate around the scanner, exposing the detectors. In newer versions of the scanner, you have a source of radioactivity, like a germanium source. Germanium 68 decays by 511 keV, and it has a very long half-life. So you put that source inside on the scanner, and it's center of the scanner, and floods all the detectors and sees what's the variability in these detectors, and directly calculates what is the current reading versus the lower and upper limit. And if the values fall within these limits, then it will tell you that the scanner is ready to be used for clinical purposes. On a daily basis, you must perform this test so that you have confidence that the scanner is working properly before you go ahead and put it in clinical use. This would then, you can take a look at the sinograms that are generated, and if all the sinograms look the same, then that means that the scanner is performing properly. Like I said, this should be done on a daily basis. On a quarterly basis, you should calibrate the machine. This transformation of activity concentrate to counts per second to activity concentration. You take a phantom, you fill it with water, and you spike it with a certain amount of radioactivity. You know exactly what's the activity concentration. You then scan that phantom in the machine, and then you correct it for attenuation, scatter, dead time, what have you. And then you run an algorithm that is already available on the scanner that then says, how many counts am I seeing? And then transform that to activity concentration, because I know what's the activity concentration in the machine. And then it says, if I have so many counts per second, and all of these should have the same number of counts per second, of course, with noise applying, then they should all have the same activity concentration with noise applied. And that mapping between counts per second to activity concentration is the calibration that needs to be done on a quarterly basis, at least on a quarterly basis, because we know that the scanner vary from time to time, and you need to just make sure that the scanner is properly calibrated at the day that you are imaging the patient. On certain scanners, such as Siemens machine, this calibration is done every day as part of the daily QC. When this is being done, it is done at that time also, because they have a germanium phantom, and germanium can be used also to calibrate the machine accordingly. Like this here is the germanium phantom. You place it in the scanner and you image it, and it will generate a calibration factors for you. This is here the results of the calibration factor. And you can see here the factor is coming out saying, for the different slices that you're seeing across the scanner, after obviously we correct for the sensitivity for the various slices. There are also approaches to check the scanner performance. We at MD Anderson, we use the ACR. This is the American College for Radiology. They use this JZAC phantom. We fill it and we assay the activity, put in the spheres a certain amount, in the cylinders a certain amount of activity compared to the background. We do that based on a certain table that you see over here, and then we image the different parts of the phantom. You can see here contrast, cylinders of different sizes, so we can assay the effect of partial voluming with different size lesions. We can look at the uniformity section of the phantom, as well as assaying the resolution by looking at cold rods in this case. These rods are of a fixed diameter, and we can see what is the smallest size rods that can be seen on this machine. We can also assay the alignment of the PET and the CT by looking at the PET image when it's fused with the CT image. Do they match each other or not? So we can assess the scanner alignment also. So on a quarterly basis, we do the calibration and the verification by looking at all of these type parameters. Now, on an annual basis, there are a bunch of tests that can be done. We know about NEMA. These are very extensive tests that can be performed, but they are really very extensive and might be very difficult to be done. AAPM, the American Association of Physicists in Medicine, has a task group report, task group report 126. I had the opportunity to lead that group, whereby we developed certain tests that can be done to assess the scanner performance. The ACR, like I said, the American College of Radiology has come up also with certain criteria that will be soon published to recommend what tests should be done on a PET scanner to ensure that the performance of the scanner is functioning as you would expect it to function. Or you can have your own set of tests as long as they satisfy your own quality assurance and quality control type program. Now, we talked about the PET part, but the PET is no longer a PET only. There is a CT component to the PET scanner. So you need to also perform a bunch of CT tests in order to ensure that the CT component of the PET CT scanner is working properly. And these would follow the standard CT type test. You know, you do a tube warm up, you perform an air cal, and then you put in a water phantom there that would measure, look at the CT number linearity. You draw a region of interest in the background, which is air and water and an acrylic, just to see if these values are consistent and they are always the same. Because as we said, the CT image is then used to be transformed to correct the PET data for attenuation. So you want to make sure that these CT numbers are accurate accordingly. We also check the uniformity by looking at the water section of the phantom, drawing regions of interest to assess and make sure that the CT number of water is constant. You know, the CT number of water should be 0 with a certain standard deviation of about, 5 plus or minus 5 CT Hans per unit. And you can see here the values in the different regions are within that particular expectation. And we look at also low contrast just to make sure that we can also see small objects within the CT scanner, because, like I said, the CT image is being used for attenuation correction. We also check to see if there are no ring artifacts on the CT image by acquiring multiple slices of the phantom and making sure that such ring artifacts do not exist in the image. And if they do, then we will make sure that the CT scanner is attended to and that artifact is no longer there. Like I said, the dose calibrator is the Achilles heel of the PET scanner. So you also need to have a quality control program for your dose calibrator. This is standard, the same quality control that you would use for a gamma camera. You need to do on a quarterly basis the linearity of your dose calibrator. You need to do constancy on a daily basis by putting the sources that are standardized sources and measure them under different setting of your dose calibrator just to see if the value is consistent. Like you take a cesium source and you measure it under, let's say, the F18 setting, under the cesium setting, under the cobalt setting, and so on and so forth. And then you obviously on an annual basis perform an accuracy whereby you take a standardized source. Here in the United States, we use the NIST source, National Institute of Standards and Technology, whereby they make sources like this is the center here in the United States that says a 1 kilogram is this, a 1 meter is that, a 1 millicurie of cesium-137 is that. So we buy a sample and we put in a dose calibrator, and we need to make sure that it measures what it's supposed to measure after doing the necessary decay correction. And if you do all of that and everything is according to your expectation, then you should have an accurate quantification, and your SUV and the assessment of your image should be reflective of the true biological nature or physiological nature that is in the patient. Thank you very much, and I'll stop here. And this time I ended on time.
Thank you, Professor.
Any questions?
Yes, we have the last one that we didn't answer.
Yeah.
It was, what measures can be taken in PET to reduce organ motion during the scanning process?
So my next lecture is about advances in PET, and it will be about what kind of correction techniques can be applied primarily to correct for various type challenges. One of them is this motion artifact, and I will show ways and means that we can correct for that. As I had mentioned, there are two different types of motion between the PET and the CT. So there's be misalignment, and then there is motion during the PET acquisition, and I will show how we can correct for these things.
Okay, thank you. And another one is, what are the advantages for the image reconstruction, comparing time of life and conventional mode?
Perfect question. Also aligns with my next lecture on advances in PET. I still consider time-of-flight imaging is part of the advances in PET, especially that there are still BGO scanners out there, and people that buy BGO scanners cannot do time-of-flight. So I will describe again what time-of-flight is and what is the advantage of time-of-flight and how does that has implication of image reconstruction. So bear with me up until I do my last lecture, and hopefully that will answer the question. Now we're going to be talking about advances in PET-CT, and these advances has, some of them are rather very new, and some that have been around for perhaps maybe a decade. But I like to put them all together as advances since, they are different than the standard PET imaging type approaches that we have discussed before. So I'm going to talk about motion suppression and how can we correct for that, time of flight and PSF, large axial field of view, continuous bed motion approaches. I'll talk about digital detector, silicon photomultiplier tubes, as well as talk about new reconstructions such as these regularized reconstruction. So let's start with motion suppression. When we talk about motion, there are two different components of motion. Like I said, there is motion during the PET image, which we call that motion blur. And then there is the mismatch between the PET and the CT that we talked about before. So here you go on the left side is that if an image, if there is an object that is moving and you acquire it during the time that it's moving for a long period of time, spheres will appear as oblong, but in reality, what we want to see is what you're seeing on the right side, that these spheres appear as spheres and you capture them as they are moving up and down. Otherwise, if you don't do so, the images will appear blurred and there will be underestimation of the activity concentration. Now, how can you do that? We do that in gating the PET data. We acquire multiple images of the object as the object is moving. So again, assume here that this is the patient breathing cycle shown in blue. You can divide the PET data in different segments. So segment 1, segment 2, segment 3, all the way. In this case, we're dividing the PET breathing cycle into 8 segments. And we're saying PET data that's acquired in segment 1 in the first breathing cycle is at the same anatomical location as the PET data in of the first segment, but second breathing cycle. So you can see here, the PET data is being added together from cycle 1 and cycle 2 for segment 1, segment 2, segment 3, and so on and so forth. And you repeat that for multiple breathing cycle. This is known as gated PET acquisition. In this way, rather than get one PET image that's blurred, in this case, because we have 8 gates, we will get 8 images, but each image will be without much blurring, only the blurring during the gate itself. But obviously, it will have 1/8 of the image signal intensity. So in as much as I have reduced the image blurring or motion artifact, I have now reduced also the signal intensity because I have now shorter acquisition type duration. Now, when you do that, you need to match the PET data with its respective CT data. So also the CT needs to be acquired at multiple locations of the breathing cycle. We call that 4D CT. And in this way, you acquire 4D PET with 4D CT, because fourth dimension is the time in this case, and you match each bin of the PET data with its corresponding CT bin. And there are ways to do that right now on most consoles of the PET-CT scanners. And you will end up with lesions rather than them being blurred like you see on the left side. They will be better circumscribed, that is seen on the right side. And like I said, you can see this motion for the different gates as the tumor is moving up and down during the PET signal. So you can see the CT has multiple CT scans there, and you can see the PET has also multiple PET scans there. But again, what you see here is that the image becomes noisy because I have reduced the number of counts by now I have 1/8 of the number of counts. So one way to recover and make the images to be less noisy is to take all of these images and then register them to each other. So you do that in image space. So you take all these 8 bins, register them to each other to generate one final image. Now, obviously, for brain imaging, that is rather very easy because the brain is considered to be a rigid object. And anyway, the structures of the brain does not move inside the brain. But for the chest is moving up and down, and the object is not considered to be rigid. So there, the registration is called a non-rigid registration, which is a little bit more complicated type registration, but definitely possible. The approach of doing that in image space is known from one manufacturer, General Electric, in this case, known as Q-freeze. And the other approach from another manufacturer, such as Siemens, they call it OncoFreeze, which is basically during the image reconstruction, the registration is being performed. So rather than registering images, this registration is done during the image reconstruction. So it's done in sinogram space in order for us to generate the final image without any noise content, as well as no motion content in the final image. And to show you the result here, this is the static image. On the left side, you can see the tumor is distributed, more oblong in this case. When we are registering the images using the Q-freeze type approach, you can see the tumor is much more clearly circumscribed, whereas in the OncoFreeze, also clearly circumscribed, reducing motion, and there is no noise in the image. You can see the noise in the image on the left side is similar to the noise that is in the middle image, similar to the noise that's in the right image. There's another approach whereby we can do that without applying image registration, because sometimes the image registration is not very accurate and by itself introduces another artifact, is that we know that the breathing cycle is not actually cyclical it's not like a sinusoidal type motion, but rather the breathing cycle has an inspiration phase and a long expiration phase. So people spend more time at end expiration than they are at end inspiration. And perhaps because the end expiration is a quiescent phase, so you take a breath and you rest more at the end expiration. So that time is longer. As you can see here in this cycle, that time is longer than that time. So perhaps the PET imaging should be done during that time only. You can do that in time, or you can do that in amplitude, depending on the manufacturer. GE does it in time, Siemens does it in amplitude, and they have different names for it. They call it Q-static for GE, they call it HD chest in Siemens. But the idea is now, rather than acquiring one bin, which is a much noisier image, is we're acquiring over the quiescent part of the breathing cycle, because the patient is not constantly moving. There is only motion during the initiation of the breathing cycle, but during the quiescent phase, there is relatively very little motion. And you can do that and generate the resultant images. And you can see here on the left side, without motion suppression on the top panel, and with motion suppression, this is Q-static on the GE side. On the right panel, the HD chest without motion suppression on the top panel, and on the bottom panel, you can see here these lesions to be much, much clearly visible as compared to the top panel according. But both can do a very good job because it's the same technique, but they call it slightly differently. But here also, we are only looking at a portion of the PET image, not all of the data of the PET image. And of course, you need to match that with the respective CT for that purpose. Now, how do you know when you are in the breathing cycle? So you need to capture the patient breathing cycle. Usually, we used to do that by using external devices, such as looking at an infrared camera with a block on the patient chest, or we use what we call a strain gauge, like a belt that is put around the patient. And as the patient breathing in and out, we will measure the patient breathing cycle. But these are relatively cumbersome and difficult to use and require a technologist interactions and so on and so forth. More recently, the suggestion is to use the PET data itself to generate the patient breathing cycle. Because as the patient is breathing, the PET data that you are acquiring is also moving up and down with respect to the detectors itself. And we can utilize what we call data-driven gating for generating the patient breathing cycle. And there are several techniques for this. You can see here, as the patient is breathing, the PET data will capture the patient breathing cycle. This is here just showing you the situation from a visual perspective, but this is here the resultant reconstructed images. This is the same slice, physical slice, and you can see at time point 1, at time point 2, at time point 3, there are differences. That there is a lesion coming into the slice and it's going out of the slice. There's a lesion coming into the slice and going out of the slice. Whether I do that in image space or I do that in sinogram space, this is also can be captured. And from these images or sinogram, I can create these breathing cycle of the patient and then use that to gate the PET data accordingly. There are also multiple techniques to extract the breathing cycle from the PET acquired data. There are multiple techniques that have been developed and utilized. We're not going to get into the details of that. But that's correcting for motion during the acquisition. Now, how about the mismatch between the PET and CT? You remember I said that the CT is relatively very quick to acquire, so it's acquired in a single phase of the breathing cycle, whereas the PET data is acquired over multiple phases of the breathing cycle, and that causes this mismatch that we had mentioned previously. Now, one way to correct for this is that since the CT data is acquired over one phase only, like you said here, like one phase only, this phase or this phase or this phase or this phase or this phase. How about we then acquire all of these phases and then average them all out to create a CT that looks like as if it is the PET data that is acquired over the whole breathing cycle in this case. So that's what we do here by acquiring multiple CT scans and then averaging all of these CT scans together. And then we will create what we call an average CT so that then we can match the CT to the PET data. So now you can see here, the CT is an average CT. The CT here is different than this CT. You can see here, the liver is shown differently than it is shown in that because it's the average CT. And then we can use this CT to correct the PET data to remove that particular error that we have been talking about. Now, of course, if you want to remove the mismatch between the PET and the CT, you can acquire also the PET data at the end phase of the breathing cycle. You say, okay, I'm acquiring PET data only in this particular part and try to match the CT to make sure that the CT is acquired at end expiration. Now, you can tell the patient as you are going to acquire your CT scan is to take a breath and then blow it out and then hold it. So we are holding the patient at the end expiration. We acquire the CT and then we are acquiring the PET data during the quiescent phase of the breathing cycle. And then they will be matched with respect to each other. Now, sometimes that is not really very easy to do. Patients are really sick. They don't follow instructions very well. And whenever we try this, you will still see that the PET data is not properly matched with the CT data. So this is still an area of investigation that is currently going on if you want to do it in this approach. But for the PET CT and average CT, whereby you are matching the PET and the CT data together, are available on scanner on the various manufacturers scanners accordingly. Let's talk about time of flight. You remember I had mentioned that in regular acquisition, you cannot tell really where did the annihilation event occur along the line of response. But with time of flight, you are capturing the time of arrival at this detector and the time of arrival at that detector. And it's that time difference will help me to identify, to pinpoint where is the event occurring along the line of response. Now, of course, if I know it exactly perfectly, then I will know this exactly at this specific location. Because if this detector detects the event a couple of seconds before or a couple of picoseconds before this detector, then I can really pinpoint it along that line because I know what's the distance between this detector and that detector. And I know that these annihilation photons are flying at the speed of light, so I can determine exactly the location. The problem right now is that the accuracy of capturing the time of arrival in this detector and that detector is not exactly perfect. Now, of course, there are electronics that can make it down to the femtosecond, but obviously these cost a lot, and I need to do that for every coincidence pair. So right now, what we do is we have capabilities on PET scanners down to the picoseconds. And when you do it down to the picosecond, that still gives you an error in positioning the location of the annihilation event down to centimeters rather than, this distance between detector 1 and detector 2 here is in the order of tens of centimeters. Like I said, the scanner has a bore of about 70 centimeters. The detectors are usually at a distance of about 1 meter from each other. But now we're cutting it down to less than few centimeters. So that will help me in identifying where did the event occur more accurately. And this has a ramification on the resultant signal to noise ratio in the final image. So just to give you empirically, we have shown previously, not we, the field has shown previously that the signal to noise ratio with time of flight imaging has an improvement over the conventional signal to noise ratio with the difference of the square root of the object diameter divided by this mispositioning error. Okay, this mispositioning error, delta X, comes from the mispositioning in timing. We don't know exactly the time of arrival. So right now, scanners that are available on the market have timing resolution accuracy of about 500 picoseconds. This is in nanoseconds, so 500 picoseconds. That gives me a positioning error of about 7.5 centimeters. The most accurate timing resolutions that we have from PET scanners are in the order now of 200 picoseconds. So we've cut down from 7.5 centimeters down to about perhaps maybe 3.5 centimeters. And that, like I said, has ramifications on signal to noise ratio depending on the object size. You can see the signal to noise ratio is improving from 1.1 to 1.6 to 2.1 to 3.7. But that improvement increases even more when you're doing large objects, because large objects have more distance through which the line of response is passing. So larger objects will benefit more from time of flight imaging than smaller objects in this case. And that's why, particularly here in the United States and particularly in Texas, we have large patients and they will benefit a lot from time of flight imaging because we can have better signal to noise ratio. We can see the signal compared to its background much clearer. So the tumors appear by far more clearly circumscribed and their values are higher compared to the background. So the physicians can easily see them and manipulate, manage the patients accordingly. You can see from this description in general is that if I can get the time down to really very, very accurate, then I can pinpoint the position exactly. And that means, obviously this is approximately, that means as if the signal to noise ratio becomes completely, infinitely better than it is in conventional perspective. But that means that if I know exactly where every annihilation event occurs, then I really do not need to do any more image reconstruction because I can now build my image point by point as these events are occurring. And there is no need anymore whatsoever for image reconstruction. We are not there yet, but there are designs of PET scanners whereby we're cutting the timing resolution from hundreds of picoseconds down to tens of picoseconds. And hopefully that will result in better and better image quality. Here to show you results of that, these are non-time of flight imaging versus time of flight imaging. You can see as if they look the same, but in reality, if you look carefully, you see things that are better with time of flight compared to non-time of flight. And that's what I was talking about, the signal to noise ratio component. Again, you look at the bottom panel, you see here, you can see these lesions better, and accordingly, their SUVs are higher also accordingly. This is the same slide that you showed. This is with time of flight on the left, without time of flight on the right. We've talked about point spread function reconstruction also, and I had mentioned that we can improve it. If we know the degradation from the center of the field of view to the edge of the field of view in image resolution, then I can build that as part of the reconstruction algorithm and recover from that resolution loss. That is what is known as resolution recovery, and now is available on all manufacturers. PET-CT scan, at least General Electric and Siemens, can recover from resolution recovery type issues. And I showed you this slide before. However, there are some problems associated with that related to ringing artifacts known as Gibbs artifact. When you correct for this, sometimes you introduce another artifact. You overshoot at the edges of where you are correcting for such loss of signal intensity. The next item that I want to mention is this large axial field of view. This is currently the area where all the innovations in PET imagings are happening. Regular PET scanners used to have an axial extent of about 15 centimeter in the axial direction. We used to call that whole body imaging because the patient then will be translated and we image different parts of the patient, compared to what we are calling now total body imaging, whereby the scanner has a very large axial extent covering the whole patient. And in doing so, the sensitivity of the scanner will be much higher. Obviously, you can image different parts of the patients in one shot. You can see here the sensitivity is by far higher than it is in regular standard whole body type imaging. And because of that, rather than image multiple bed positions to cover the whole patients from, the eyes to the thighs region, you can image that in one bed position in order to get the final image. So there are several advantages. There are higher sensitivity. There are larger coverage, so that implies that there is faster scanning. However, the challenges are these machines are very costly because there are many, many detectors, and the most expensive part of the scanner is the scintillating material, especially if you're going to go with LSO type detectors, because these are very expensive. And then you might need larger rooms to place these scanners in the facility itself, because they are physically larger type systems. There are also several applications that these type systems can be used for, primarily from doing tracer kinetic modeling. They are used better for pediatric imaging because you can do the image relatively very quickly rather than image on multiple bed positions. And pediatric patients are usually very lethargic and they do not like to stay inside the scanners for a long period of time. So usually the imaging can be done relatively very fast in that way. Currently, there are 3 manufacturers that do this. United Imaging here at the bottom right generates a scanner that's 2 meters long, which is really amazing in this case. Siemens has just recently come out with a machine that is 1 meter long rather than 2 meters long, 106. This one here is 194 or 196. And GE is just recently introduced a 32 centimeter long axial extent with the idea that next year they will have a 128 centimeter long also scanner on the market. Just putting some performance characteristics between the Siemens machine that they called Quadra versus the Explorer machine versus this GE Omni scanner. You can see here the axial extent 106 centimeter versus 194 centimeter versus 128. There is a scanner from University of Pennsylvania. It's not commercially yet available, but it is a design that has already been around for quite a while. And you can see here the performance characteristics of these scanners, the sensitivity of these machines, 174. And this machine still does not have that value available because there is no such machine yet still out there. But really, very, very impressive type systems compared to the ones that we currently have in the clinic. We here at MD Anderson have just recently installed one of these Quadra type scanners, and I will show you the performance of this machine. Luckily, the room size, because it's a 1 meter machine, is the same as the other room sizes. So there is really no need for a larger space. So we could take one of our old machines and put a new scanner instead of it without much fanfare. Here is to show you our current scanners that had 15 or 20 or 25 or 30 centimeter axial extent. The y-axis is the sensitivity. The x-axis is the axial extent of the scanner. Most scanners have sensitivity in the range of 7 or 14 or 25 centimeter. We have 3 of these scanners in our institution, but you can see the difference between 7 to 14. We'd say, oh, wow, that's double the sensitivity. Or this is 3 times that sensitivity, which is really amazing. We don't have a 30 centimeter scanner, but that is something that also GE has recently released with a 6-ring type scanner. And again, you know, you would look at that and say, you know, 30 sensitivity with 30 units compared to 7 units. That's like about, you know, like 4 times or something like that. It's really very, very impressive. But when you put that into perspective, when you look at these others machine, this is the sensitivities that we're talking about. This is before 15, 20, 25, 30 versus the 1 meter machine that we're talking about. The 1 meter machine can be operated in 2 modes. You remember, like I said, 2.5D versus a completely 3D. This is when it's done at 3D, and this is when it's done at 2.5D. And you can see here that the sensitivities that we're talking about is completely and utterly out of realm compared to the other type scanners. So with that type systems here, you can inject less activity, you can scan faster, you can get better, completely better image quality, and so on and so forth. This is here the scanner performance when we look at another metric known as the noise equivalent count rate. This is the 15, 20, 25, and 30. And again, when you compare them with the current machine at 1 meter with 2.5D versus the completely 3D, you can see that the performance is very, very different. Now, yes, the performance is very different for different activity concentration, but what is the value that you usually do whenever we're imaging a patient? We're in this range when you're imaging a patient, this dotted line, and you can see still at this range here, when you do full 3D, the amount of noise equivalent count rate that you get is by far higher than you would have in your standard type scanner. So we are really very eager to start to use our machine on our patient when it's fully in 3D. Currently, we are operating it in 2.5D because 3D, full 3D is not yet available from the manufacturer. The manufacturer decided to do 106 centimeter only by looking at various patient habitus, you know, the size of patients, and realizing that 106 always covers from the top of the head down to the pelvic area, which is the majority of when PET-CT imaging is done. Most PET-CT for oncologic type applications are done from the top of the head down to the thighs, because nobody is interested very much in the legs and so on and so forth. So in 106 centimeter, even if you have a very tall patient, you should be able to cover that with a 106 type centimeter patient. These are some of the patients that are coming out from our scanner. On the top side is the standard PET scans that are done on patients using the standard PET machines. And on the bottom side is the Quadra type scanner. And you can see, you know, these images here really look less noisy because you have much more sensitivity. So the images look by far easier for the physicians to look at. Look at the liver here, relative noise compared to the liver here in relative noise. These are patients that are relatively big, 91 kilogram type patients, injected with about 10 millicuries of activity. Another patients here, 100 kilogram patients. You can see the noise in the top image versus the noise in the bottom image. You can see here, you know, the patient was breathing heavily in this case. You can see here the liver has a silhouette because it has two, like the liver is expanded between the two breathing cycles, you know, inspiration and expiration. But you can see the expiration more so than the inspiration because patients stay more at the expiration level than the inspiration. Again, here a patient scan. This is a 62 kilogram, relatively small type patient. In this case, still with 10 millicuries injected. You can see these images really very, very nice. Look at the vertebral column here. You can see really easily. So these images are now starting to approach as if like they are anatomical images rather than just functional type images. And another case, in this case, this is another 100 kilogram type patient. So what are the potential uses of these type large scanner? Now, obviously, if you look at the signal to noise ratio, it's usually the square root or constant multiplied by the square root of the sensitivity, the activity, and the time. Usually that's your signal to noise ratio. And, you know, one thing that everybody would look at is to start to reduce the scan time, because you have a very large sensitivity. You can reduce the scan time and still get the same signal to noise ratio as you used to have before. So initially we used to scan with 10 minutes. Now we're looking at 8 minutes. We're going to look at 6 minutes or 5 minutes. This is a total scan from top of the head down to the pelvic region in about 5 minutes scan. You know, I started my career back in the late 90s, and it used to take us 1 hour to do a PET-CT scan. Now it is going to be down to about 5 to 10 minutes to do a full PET-CT scan, which is really amazing in this case. Now, of course, as you reduce the scan duration, the noise will still be higher, will get a little bit higher, but we can mitigate that by filtering the images a little bit. We will reduce the reconstruction time because obviously there will be less number of events to reconstruct. The reconstruction here is a line of response type reconstruction that depends really on the number of events that are being detected in this case. But then if you reduce your scan time so much, then you have to deal with the upstream part. As you know, we said that a patient needs to be injected, wait 1 hour to then be imaged. So if we're still needing to wait 1 hour before we image the patient, and the imaging is now 5 to 10 minutes. We need to have lots of rooms whereby you can occupy, whereby you have the patients wait up until the activity uniformly distributes in the body. So we're going to have lots of challenges in having to have lots of injection rooms in that regard. The other approach is, so here you can see different scan duration. The top panel is 8 minutes. The middle panel is 4 minutes. And you can see the 4 minutes is with a noisier image than the 8 minutes, as you can see here. But if I take the 4 minutes and filter it a little bit, you can see here the image that is at 4 minutes is very similar to the image at 8 minutes, slightly more blurred out, but not really that much. And these are really very, very good images. It's like a 4-minute scan, you know, being acquired from eyes to thighs, which is really amazing. That's another case, 8 minutes versus 4 minutes without any filtering, because this is a relatively small patient. So we really don't need to filter much. That's about 40 kilogram patient. So there's no much, you know, the signal even at 4 minutes is enough for me to generate a good quality image. The other approach is to obviously reduce the injected activity and say, you know, because the scan is very sensitive, so I am reducing A, but because S is very high, then the signal to noise ratio will be the same as it used to be before in regular type systems. And like I said, initially we used to inject 10 millicuries. We're looking to inject less, in 6 to 8 millicuries. I know that in Europe, usually they inject 5 millicuries, but our patient population is relatively much larger. And but with this machine, we can definitely reduce the injected dose by half, if not make it a third, and still have good quality images. That reduces the effective dose from 7 to about 4.2 when we go from 10 millicuries to 6 millicuries. And also, it has a cost type perspective. Right now, the doses that we pay for are per 10 millicurie dose, but I am sure if we start to ask for 5 millicurie doses, then we can cut our cost for the dose itself by a large amount too. So there is an opportunity in that regard. But again, reducing those might run you into noise, so we can use the filtering to improve the image quality. And I will show you some images in this case. This is a 5.6 millicurie injected activity. This is with no filtering, and you can see the images really look very well here. The CT on top, the PET, and the fused type images. And this is a scan that was done in 8 minutes, injected with about 5.6 millicuries. Really, really very high quality type scans. When we look at a 5 millicurie scan with about a 60 kilogram patient, something similar to what you would see in Europe in this case, the patient population and the activity, and then me trying to reduce the scan duration, 10 minute, 8 minute, 6 minute, 4 minute, 2 minute, 1 minute, half a minute, 15-second scan. This is really amazing. And I'm just filtering it with 2 millimeter Gaussian. These are MIP images. These are really, really phenomenal type scans. So now we can do PET scans that are really very, very fast and relatively with low dose without much fanfare at all. We can also leverage, all the images that I showed you before are with FDG, with fluorine 18. The branching ratio of F18 is about 97%, meaning that, you always get annihilation photons for every disintegration. But in other type radioactive compounds, such as Y90, whereby you get only 30 disintegration for every million, 30 events for every million disintegration, or when you use copper 64, which has a photofraction of 18%, then you need to have a very good sensitivity scanner so that you can generate good image quality with reasonable amount of injected activity and scan time in that regard. So I show you this image here. This is from an old type scanner that we have, the MCT. This is from Siemens. Sensitivity is relatively low. This is gallium-68 images. And comparing the same patient scan now using copper 64. Copper 64 has a relatively very little branching ratio, so there is very little annihilation events being generated compared to the gallium-68. But this is a 10-minute scan, total 10-minute scan. This is 3 minutes per bed, and this is like about 4 or 5 bed positions. So you can see, even with a 10-minute scan here, 17% of the signal is being detected because of copper 64. The images really look very good, and you can see so many different lesions compared to when it was done using gallium-68. Now, obviously, when you have a large axial extent, you can use this to see the distribution of the compound in the patient as the activity is being distributed. And for that, then you can calculate different values other than SUV. You can calculate Ki, K1, volume of distribution, or volume of the blood. These are really very different type outcome measures compared to the semi-quantitative measures that we currently use in PET imaging. And I show you here these images. This is from a previous publication showing the standard SUV image, or you're looking at the Ki image, or the blood volume image, or what we call a K1 image. And there is a difference between Ki and K1 type images, as you can see from the resultant images. This is true quantitative type imaging, and you can only do that by looking at the compound as it's distributing in the body over time. Now, of course, when you do such imaging, the imaging time has to be longer so that you can capture the distribution of the compound over the time course of its distribution. But these images open the door for you to look at many, many different variables in PET imaging that were not possible in standard PET image type approaches. So like I said, you can look at biodistribution, or you can look at the symmetry. I want to show you these slides here, whereby you can see the distribution of the compound. This is in 2-second frames. You can see it in the lungs, in the kidneys, in the heart, and so on and so forth. But because the data is acquired at a very in list mode, whereby I can then rebin the data whichever way I want, and I generate picture at a very, very short duration and still have good quality images. You can see here, as the activity is in the line being injected into the patient, it goes into the patient, it goes to the heart. You can see now the heart beating, and also at the same time, the patient is breathing. So you can see both motions at the same time. This is not possible to see at all in PET imaging, except in such type scanners, which is really, really very innovative and something that is unique for this type of systems. Now, there are some ethical dilemmas, especially in sites like ours, whereby we have both type of scanners, whereby obviously if you put a patient on this machine, you can see so many things and you can manage the patient in a much more elaborate manner compared to old scanners, whereby you cannot see everything. So which patient do you put on this machine versus other machines, and so on and so forth. And this is something that we're trying to figure out here and try to deal with on a regular basis. The other thing I wanted to mention is continuous bed motion. So these are only available from Siemens. You can see here, this is the bed moving in a continuous fashion compared to a step and shoot type approach. The idea is with a continuous bed motion, the patient is uniformly moved through the bed as like it is on a CT scan when it's acquired in helical mode. And this is much more soothing to the patient and gives you better uniformity across the axial extent of the scanner, only available from one manufacturer compared to other. This gives you also more flexibility in identifying where you want to start and where you want to stop with flow motion technique, which is the continuous bed motion, compared to a step and shoot type approach. It also has some ramification on CT dose, because in CT, in step and shoot, you have to define the regions based on bed positions, 1 bed position, 2 bed position, 3 bed position. So you are limited by where you start and where you stop. Whereas in a continuous bed motion, you can start and stop at any location you want, inclusive of the CT. So in this case, if this is a female patient and you didn't want to image the breast here because you want to reduce the dose to the breast, you cannot do that on a PET CT scan because you have these 3 bed positions. But let's say you want to stop at this location, you cannot do that in a step and shoot mode, but you can do it in a continuous bed mode. Some advantages in that regard. More recently, in the past, perhaps maybe 7-8 years now, we've replaced the photomultiplier tube, the analog photomultiplier tube, by digital photomultiplier tube. So I could show you here. In the old days, you know, when an annihilation photon occurred, you could try to triangulate where the light is that is coming down by saying, okay, this photomultiplier here is getting more light than this one, than that one, than that one, than that one. And as such, perhaps the event is more central to this particular location than other locations, and so on and so forth. And this here shows multiple such events being recorded by various type detectors. Whereas in digital type detectors, you are replacing this photomultiplier tube by silicon photomultiplier tube, and these are very, very small sizes. So whenever an event occurs, it can be directly channeled to a specific location so that you can identify the event more accurately within the spatial type coordinate. So you can see these are the previous analog type detectors from before. And these are being replaced now with these digital detectors that I'll show you a slide for. This here is a comparison between standard analog photomultiplier tube versus the silicon photomultiplier tube. There is also an avalanche photomultiplier tube that at one point was being developed but has been discarded. And you can see here, as far as the gain between the standard photomultiplier tube and the analog and the digital photomultiplier tube, they are the same. The rise time, as far as the speed by which they do their work, is relatively very similar to each other. One very important component is the magnetic susceptibility, meaning that can you put such a detector in an MRI scanner? And this whole idea of using digital detector was originally developed for PET MRI, when PET MRIs were being developed. And later on, because we saw that, you know, the silicon detectors have improvements as far as resolution is concerned, we said, why don't we just utilize these silicon photomultiplier tube in regular PET CT scanners rather than the standard photomultiplier tube? Now, of course, they are a little bit more expensive than regular photomultiplier tube, but they give you better resolution because I can pinpoint the event more accurately. You can see here magnetic susceptibility. PMTs do not work in an MR, but they do work very well for a silicon photomultiplier tube. So this is now the digital detector here. It's a silicon type detector. And see, it's attached to the block of the scintillators, and then they have a light shield so that the light does not escape. I will show you here, I was in a meeting whereby you could see easily these digital detector and the silicon photomultiplier tube and the scintillator, how they will attach to each other. These are usually glued to the scintillator using an optical glue there, so that the light that gets to be generated from the scintillator can be channeled easily down to the silicon photomultiplier tube without much difficulty. Different scanners then build these detectors. So you can see here, this is the digital detector here, the scintillator and the silicon photomultiplier tube. And then we can put so many of them back to back. So it's 5, 10 centimeter, 15 centimeter, 20 centimeter, 25 centimeter. And like I said, General Electric developed another one, which makes it a 30 centimeter, and so on and so forth. This is an image here that comes from an analog type detector versus a digital detector. This is not a direct comparison because the crystal sizes are slightly different. But the idea is that you can see more the digital detector in the 6.4 millimeter elements in the phantom, better on the digital detector rather than on the analog detector. You can also claim to see the 4.8 millimeter elements better on the digital detector compared to the analog type detector. But that's really not a fair comparison because of this difference in the detector element size in this case. Lastly, I want to end with new reconstruction algorithms that are available. We talk about regularized reconstruction. As you know, in iterative reconstruction, this is an estimate of the truth, and we iterate in order to find the final image that represents really the acquired data that we had acquired. So when we do iterations, so we say, okay, the first iteration, this is what the image looks like. The second iteration, you remember I showed you before iterations and subsets and stuff like that. This is generating images in every iteration and say, does this image truly represent the data that we had acquired or not? And most of the time, as you iterate further and further, the images becomes noisier and noisier and noisier. Most of the time, we don't iterate for a very large number of iterations because you don't want to create images that look very noisy. We stop usually at a relatively small number of iterations, although we know that when we do so, we are not reaching convergence, which is the true value in the body as far as activity concentration. Usually iterative reconstruction needs to converge, needs to reach convergence. But as you iterate further and further, you are also increasing the amount of noise in the resultant image. So most of the time, when we generate our PET images using iterative technique, we stop early in our iterative reconstruction in order to generate images that are relatively less noisy, but as close as possible to the truth. Here in this case, we're looking at a lesion showing 8.2 SUV, but we know in reality, this is not the truth here. The truth is somewhere between perhaps 12 and 13 SUV, but we know this might be very high because of noise, but we don't know what the truth is in this case. That's why new reconstruction algorithms have been generated, whereby as we increase the number of iterations in subset, which is increasing the noise in the image, we are obviously getting closer and closer to the truth. This is the contrast recovery, meaning how much are you getting from, with respect to the truth? You're getting from 30 to 40 to 50 to 60% of the truth, and so on and so forth. Right now, we usually stop at an early number of iterations in subset. And what we really want is to move all the way up to the convergence, but without this noise. We want it to be at this noise level. And that's what these regularized reconstructions allow us to do. So I will show you, this is here a phantom scan with 5 minutes down to half a minute without regularization, without suppressing the noise in the image as we iterate further and further. And this is with noise suppression as far as regularization. So you can see the 5 minutes looks much clearer because we eliminated the noise from the image and we improved the contrast because we are recovering more of the signal in this case before and after. And similarly, looking at the contrast component before regularization and with regularization. You can see with regularization, it's smoother, but you can see more the contrast component of the objects much more clearer, even at different scan durations in this case. And when we apply this to a patient, I'm going to show you this on the left panel here, just doing what we call point spread function reconstruction or resolution recovery. This is time of flight with resolution recovery. This is here with regularization and resolution recovery. And this here is with everything: time of flight, resolution recovery, and regularization. You can see there are lesions that you can see here much clearer that you could not see in different type reconstructions. But like I said, this impacts the quantitation accuracy. So on the left side is with regularization, with regularization, and the right panel is without regularization. You can see here the SUV is higher than compared to this because you have better signal to noise ratio. You're suppressing the noise in the resultant type image. I'm going to stop here, see if you have any questions, and thank you very much for your attention.
Thank you so much for this journey on the PET. We maybe can wait a little bit more for some questions from the audience.
Yeah.
In the meantime, I have one question about the radio protection. So it is a problem. You already mentioned that hybrid modalities imply a higher exposure due to, and also the movement correction that must be that improve the quality of the images. But in the opposite part, it implies to more higher exposure from the patients with the several acquisitions from the CT. Will we be able to avoid this in the near future, or?
Actually, that's a very good question. You know, like I said, in one case where we reduce the amount of motion by acquiring multiple PETs, by gated PET, and then acquire multiple CTs and then match them to each other so that we reduce motion. The downside is I'm acquiring multiple CTs. So the patient, rather than getting one CT, now is getting many CTs, and that requires lots of exposure. That's why people were saying perhaps to suppress the motion rather than do multiple PETs and multiple CT is to acquire the PET data during the quiescent part of the breathing cycle, the end expiration part. And at that time, just acquire one single CT, but make it to be at the end expiration. So that same CT of the patient, try to do it at the end expiration and be matched with the PET data in that case. This way, you will not have any motion and you will not have the dose. The problem, however, is can we really acquire the CT at the same part as the PET data? Not very easy, and lots of work is currently going on in that domain. Perhaps with some artificial intelligence, there has been suggestions that if you acquire a CT scan, then you can modify that CT scan to generate another pseudo CT scan, and it will represent the patient at their end expiration had it been acquired at end expiration. So it will be like similar to it, although you have not acquired it.
Okay.
You know, lots of discussions in that domain.
Also, the ethical questions make us think, because with so good modalities nowadays, we hope in the future that everyone has access to the new modalities, but it will be a little bit far away in time. So
absolutely. So like an institution like ours, whereby we have several regular scanners, and now we have this really very high quality scanner, it really represents this challenge.
Yeah.
So to us here in the United States, the patient experience and these ethical questions are very important. And we are leveraging that to go to the institution to say, you know what, we want to replace our remaining 3 scanners that are in this hospital here, and we're going to buy another high quality scanner. So get rid of the remaining, we have a total of 4 in this location. Mm-hmm. So we say 3 of them are old machine, 1 of them are this super duper scanner. Let's get rid of the remaining 3, get another super duper machine. And this way, all our patients will benefit from a very high quality scanner. And since we no longer need the 2 additional rooms for the 2 additional scanner, perhaps we can use those as injection rooms. Because like I said, we are running into the problem of needing more and more rooms for the activity to distribute in the body. That is where the challenge right now is. When you decrease the scan time, you still need rooms to have people wait up until the activity distributes in their bodies. So, you know, it's a double-edged sword, as they say.
Thank you very much, Professor Mawlawi, for this great session. It was amazing.
Absolutely.
We hope to have you here with us in the next year, because it's a very good session.
You know, I look forward to that. I was telling your colleague earlier that it's so funny because in 10 days I am going to be in Portugal. Really? I'm traveling there on holiday. I am going to go to Portugal for holiday, and I'm going to go up to Porto, and I'm going to be in Lisbon. So I I will
need to
report
come
to
to
you next
Coimbra
year about my
also.
experience.
Okay, enjoy, and also give a little time to go to Coimbra.
Yeah, well, I would tell you the truth. I am driving from Lisbon to Porto, and I heard from your colleague that Coimbra is on the way, it seems. So
Yes,
perhaps
yes,
maybe
yes.
I will make I will let you know whether I am.
And compared to
I
the
have time to
States,
do that.
yeah, compared to the States, Portugal is very short. So
I know
it will
you're
not be a
saying that.
problem for you, I guess.
Yes. Again,
So
thank you very
so
much for the invite. I truly appreciate it and look forward to participate next year.
Yeah, we will be glad with that too. So thank you so much.
Thank you.